Welcome. Please take a very deep, very slow breath and simply allow yourself to settle in. Let the weight of the day gently fall away, leaving behind only the quiet space of this present moment. There is nowhere else you need to be right now, and absolutely nothing else you need to do other than listen and let your mind wander through the wonders we are about to explore. Tonight, we are going to journey together into the very fabric of existence, peeling back the layers of the visible world to uncover the hidden architecture of everything around us. In this first lesson, we begin at the very beginning. We will not start in a modern laboratory filled with glowing screens and complex machinery, but rather on the peaceful, sun-warmed shores of ancient Greece. We are going to explore the earliest whispers of what makes up our physical world, tracing the lineage of a single profound thought experiment that forever changed the course of human understanding. As we explore this together, allow your imagination to open up, preparing to see the universe not just as a collection of solid objects, but as a masterpiece of invisible, eternal pieces. Lesson 1. Early Ideas in Atomic Theory. Long before the invention of microscopes, long before the scientific method formalized our laboratories, early philosophers looked at the world and asked a wonderfully simple question. Picture yourself standing quietly on an ancient beach, the water washing rhythmically against the shoreline. Imagine bending down and picking up a single, smooth stone. It feels solid and complete in your hand. Now, ask yourself, what would happen if you were to take a chisel and gently strike that stone, breaking it perfectly in half? You would be left with two smaller stones. Now, imagine taking one of those halves and dividing it again, and then again, and again. Your mind can easily picture the pieces getting smaller and smaller, turning from pebbles into coarse sand, and from sand into a fine, powdery dust. The question that captivated the ancient Greek thinkers, specifically a philosopher named Leucippus and his brilliant student Democritus, was this: is there a stopping point? Can you keep dividing that dust forever, into infinitely smaller and smaller pieces, or do you eventually hit a fundamental limit? Do you finally reach a piece of matter so incredibly small, so perfectly unified, that it simply cannot be divided any further? Around the 5th century before the Common Era, Democritus confidently answered that question. He proposed that, yes, there is a final stopping point. He believed that all matter in the universe is ultimately composed of tiny, indivisible, and indestructible building blocks. To describe these ultimate pieces of reality, he used the Greek word atomos. When we translate this word gently into our modern tongue, it means uncuttable or indivisible. This is, of course, the beautiful origin of our modern word, atom. Think of these early atoms like the invisible, permanent grains of sand that make up the vast, sweeping desert of our universe. From far away, a desert looks like a smooth, continuous rolling hill of color. But when you kneel down and look very closely, you see that the smooth surface is actually made of countless individual, distinct grains. Democritus argued that the entire world is exactly like this. The water we drink, the wood of the trees, the skin on our hands, and the very air we are breathing in this quiet room, all of it, from a distance, appears smooth and continuous. But underneath, at a level too small for our human eyes to see, it is a magnificent mosaic of unbreakable, uncuttable atomos. Democritus did not merely stop at the idea that these atoms existed. He spent his days giving them a rich, imaginative life in his mind. He envisioned a universe where these uncuttable pieces were infinite in number and eternal in their existence. They had always been there, and they always would be. But if everything is made of the same fundamental atoms, he wondered, why does a stone feel so different from a pool of water? To answer this, he reasoned that while all atoms were made of the same fundamental substance, they must come in an endless variety of different shapes and sizes. He imagined that the atoms that make up a hard, rigid piece of iron might have rough, jagged edges, perhaps even tiny invisible hooks, allowing them to interlock tightly and firmly together, creating a solid mass that resists bending. Conversely, he imagined that the atoms making up water must be perfectly smooth and completely round, allowing them to roll and flow over one another effortlessly, like a cascade of tiny glass beads pouring softly from a jar. Crucially, for these atoms to move, to lock together and break apart, Democritus realized there had to be empty space for them to move through. He introduced the radical concept of the void, a vast, infinite nothingness in which the eternal atoms constantly swirl, collide, and arrange themselves. The idea that everything in reality was simply atoms and the void was a breathtakingly elegant theory. However, this beautiful, poetic intuition was not universally embraced. In fact, it was met with deep skepticism and eventually pushed into the historical shadows by one of the most towering and authoritative figures of ancient philosophy, Aristotle. Aristotle looked at the world and found the idea of an invisible, uncuttable particle completely illogical, and he found the concept of a void, or an absolute nothingness, deeply troubling. Instead, Aristotle favored the idea of continuous matter. He believed that the world was woven from a seamless blend of four fundamental qualities or elements: earth, water, air, and fire. To Aristotle and his many followers, a stone wasn't a collection of tiny, jagged atoms. It was simply a manifestation of the element of earth. Because Aristotle's influence was so vast, and because his theory felt much more intuitive to the everyday human experience of watching fire burn and water flow, the poetic vision of the atom was largely set aside. For nearly 2,000 years, Democritus's magnificent idea lay dormant, quietly waiting in the dark for human history and human technology to finally catch up to its brilliance. As you lie here, resting quietly, think about the immense power of that simple ancient curiosity. So you see, this isn't just a dusty theory safely tucked away in a forgotten historical text. It is the very foundation of human inquiry, the spark that eventually ignited all of modern physical science. Every time you marvel at the diversity of the materials in your daily life, from the cool, smooth glass in your window pane, to the soft cotton of your pillow, to the gentle, rhythmic beating of your own heart, you are sharing the exact same wonder that sparked the minds of those ancient philosophers on the shores of the Aegean Sea over 2 millennia ago. They did not have the tools to prove their vision, but their minds were able to pierce the veil of the visible world. They teach us that sometimes the most profound truths of our reality begin simply as a quiet thought, an imaginative question asked in a peaceful moment. By simply asking what happens when you cut a stone in half over and over again, they laid the invisible groundwork for the chemistry, physics, and biology that shape our modern world today. It reminds us that our minds are capable of seeing far beyond what our eyes can ever show us. Let us hold that magnificent, ancient thought right here, allowing it to rest gently as a complete, perfect piece of the puzzle within our minds. We have watched the idea of the uncuttable atom born in the ancient world, only to sleep quietly through the centuries. As we begin to let the shores of ancient Greece fade softly into the distance, we prepare to travel forward in time. Our next lesson will hand us the adjacent piece of this grand story, bringing us out of the realm of pure philosophy and into the dawn of modern science, where a quiet English schoolteacher will finally prove the ancients right. Lesson 2. Postulates of Dalton's atomic theory. Welcome back. In our last session, we traveled to the ancient, sun-drenched shores of Greece, where we laid the philosophical groundwork of the uncuttable atom with Democritus. For nearly 2,000 years, that beautiful idea slept peacefully in the dark, overshadowed by other philosophies, quietly waiting for humanity to develop the tools and the patience to look closer. In this lesson, we take the next step together. We are going to gently fast forward through the centuries, leaving the realm of pure philosophical poetry and entering the quiet, meticulous dawn of modern scientific measurement. We will explore how those ancient, whispered musings were finally transformed into a rigorous, verifiable scientific theory by a remarkably patient and observant English schoolteacher. As we explore this together, we will see how a quiet dedication to watching the world can reveal the deepest secrets of the universe. Our story now brings us to the very early years of the 19th century, in a damp, softly lit corner of England. Here, we meet a man named John Dalton. Dalton was not a glamorous or boastful scientist seeking fame. He was a humble Quaker and a dedicated schoolteacher with a profound, lifelong love for observing the weather. Every single day for decades, Dalton quietly and methodically measured the rainfall, the temperature, and the pressure of the air around him. It was through this peaceful, daily rhythm of studying gases in the atmosphere that he began to wonder about the invisible particles that made up the air. His patient observations led him to dust off the ancient idea of the atomos and weave it into a brilliant, formal framework that we now call Dalton's atomic theory. To build this framework, Dalton formulated a set of logical postulates, or foundational rules, that brought atoms out of the philosophical shadows and firmly into the light of chemistry. His very first postulate was a confident restatement of Democritus. All matter, everywhere, is composed of incredibly tiny, indivisible particles called atoms. But Dalton went much further. His second postulate stated that all atoms of a specific given element are perfectly identical to one another in their mass, their size, and their chemical properties. And, in his third postulate, he declared that the atoms of one element are fundamentally and permanently different from the atoms of all other elements. You might picture this concept like a grand, cosmic bakery. Imagine stepping into this warm, fragrant bakery, where the baker produces very specific types of bread. A copper atom is a specific type of perfectly baked roll. Every single copper roll that comes out of the oven is identical in weight, shape, and texture to every other copper roll in existence. However, that copper roll is entirely distinct from an iron roll, or a gold roll, or an oxygen roll. Dalton realized that the universe has a finite set of these fundamental ingredients, and while every piece of a specific ingredient is identical to its siblings, it remains beautifully unique from all the rest. This was a monumental shift in human thought. Matter was no longer viewed as a continuous, mushy blend of abstract qualities like earth and water, but rather a crisp, organized collection of distinct, countable building blocks. Dalton officially published this breathtakingly elegant system in the year 1808 in a quiet, heavily pondered book titled A New System of Chemical Philosophy. Within its pages, he didn't just define what atoms were, he described exactly how they interacted to build the endless variety of the world. This brings us to his fourth postulate, which introduced the beautiful idea of chemical compounds. Dalton explained that compounds form when atoms of more than one element combine with each other. But they do not combine randomly. They combine in incredibly simple, fixed, whole number ratios. Because atoms are solid, uncuttable building blocks, you simply cannot have half of an atom in a molecule. Nature does not work in fractions of an atom. For example, to make a single molecule of water, the universe always uses exactly 2 atoms of hydrogen and exactly 1 atom of oxygen, 2 to 1. It is never 2.5 hydrogens, and it is never 3/4 of an oxygen. It is a perfect mathematical harmony. This idea beautifully explained a principle that chemists had been noticing in their labs, known as the law of definite proportions. No matter where you find water on Earth, its chemical recipe is absolute and unchanging. Perhaps the most comforting and profound of Dalton's ideas was his final postulate regarding chemical reactions. Before Dalton, it was sometimes thought that materials could simply vanish into nothingness when burned, or appear magically out of nowhere. Dalton calmly corrected this. He stated that a chemical reaction is simply the peaceful separation, combination, or rearrangement of existing atoms. During a chemical reaction, atoms are never, ever created out of nothing, nor are they ever destroyed or entirely erased from existence. This beautifully anchored abstract thought to measurable reality, perfectly explaining the law of conservation of mass, which had been proposed shortly before by the brilliant French chemist Antoine Lavoisier. Imagine holding a deck of playing cards. A chemical reaction is nothing more than reshuffling that deck. You might deal the cards into new hands, creating new patterns and new combinations that look entirely different. But the total number of cards, the total number of atoms, remains exactly the same. The universe is the ultimate, flawless recycler. Every atom inside your body right now has existed since the dawn of our solar system, having been shuffled through stars, oceans, ancient forests, and the quiet earth, before temporarily and beautifully rearranging themselves to become you. So, you see, Dalton's postulates are not just historical stepping stones. They are the very reason we can trust the physical world. They provide an incredible sense of order and predictability. When a pharmacist meticulously formulates a life-saving medication, or when a materials engineer develops a new, lightweight battery to power our homes, they are relying entirely on the quiet, steady predictability that John Dalton recognized on those damp English mornings. They know that atoms will combine in fixed, reliable ways every single time. There is a profound comfort in this consistency. It means that the universe is not random, chaotic, or arbitrary. A glass of water poured today follows the exact same chemical recipe as a gentle rain that fell upon the earth 1,000,000 years ago. The laws of nature are steady, patient, and completely reliable. As you rest tonight, you can take comfort in the fact that the very building blocks of the world around you are following these simple, elegant rules, holding the world together in perfect, quiet harmony. John Dalton gave us the solid, unbreakable atom, bringing magnificent order to the universe and providing a firm foundation for all of chemistry to follow. For almost a century, his vision of the atom as a solid, featureless sphere was deeply satisfying. But science, like a curious mind, is always a continuous journey of looking closer and asking what lies beneath the surface. Let us hold Dalton's solid sphere in our minds for now, a perfect resting place for tonight's journey. So when we return to our narrative, we will learn how to gently crack open that unbreakable sphere, looking past the surface as we begin our study of the hidden sparks within. Lesson 3. Discovery of the electron. Welcome back to our quiet space. In our last session, we found great comfort in John Dalton's vision of the universe. We marveled at his perfectly solid, unbreakable atoms, imagining them as the absolute, unchanging building blocks of everything around us. For nearly 90 years, scientists rested easily with this idea. The atom was thought to be a tiny, featureless sphere, much like a smooth, solid billiard ball. But as we take our next step together tonight, we're going to look a little closer. We are moving into the twilight of the 19th century, a fascinating era when the flicker of gas lamps was just beginning to be replaced by the quiet hum of electricity. In this lesson, we will step into a darkened laboratory to witness a beautiful, glowing experiment. We are going to discover that Dalton's solid atom is not a simple, empty sphere at all, but rather a magnificent house with tiny, energetic occupants. Prepare to see the atom crack open, revealing the first of its hidden secrets. To understand this wonderful discovery, I want you to imagine a beautifully crafted, hollow glass tube, perhaps the size of a delicate rolling pin. In the late 1800s, scientists became fascinated with these glass tubes. Using special pumps, they would draw almost all of the air out of them, creating a quiet, empty vacuum inside. Then, they would seal a small piece of metal at each end of the tube and connect those metal pieces to a very strong electrical battery. When they turned the power on in a darkened room, something magical happened. A mysterious, ghostly beam of light would shoot straight through the empty space inside the glass tube, traveling from the negative metal end toward the positive metal end. Because the negative end of an electrical circuit is called a cathode, they named this glowing beam a cathode ray. It cast a soft, eerie, greenish-yellow glow against the glass. At first, scientists simply watched it, mesmerized. They thought it was merely a new, strange kind of light. But a brilliant, quiet English physicist named J. Thomson wanted to know exactly what this glowing ray truly was. He wondered, is it just a trick of the light, or is it something physical? To find out, he performed a wonderfully simple and elegant test. He brought a strong magnet close to the side of the glass tube. If the ray were just ordinary light, the magnet would do absolutely nothing. But as Thomson gently moved the magnet closer, the glowing beam physically bent. It curved away from its straight path, bending gracefully like a supple willow branch caught in a soft wind. Furthermore, when Thomson placed positively charged electrical plates near the tube, the ray eagerly bent toward them. In the rules of nature, opposites attract and likes repel. Because the ray was powerfully attracted to the positive plate, Thomson deduced, with absolute certainty, that this glowing beam was not light at all. It was a flowing river of incredibly tiny, physically real particles, and every single one of them carried a negative electrical charge. Think of it like turning on a gentle faucet in the dark, but instead of a stream of water, what flows out is a continuous, shining stream of pure, negative electricity. We now call these tiny, flowing particles electrons. Thomson conducted this elegant series of experiments in the famous Cavendish Laboratory at Cambridge University, publishing his groundbreaking revelation in 1897. But the true shock of his discovery was yet to come. By carefully measuring exactly how much the magnetic field bent the glowing stream, Thomson was able to calculate the weight of these negative particles. What he found sent ripples through the entire scientific world. These electrons were unimaginably light. In fact, they were roughly 2,000 times lighter than a single atom of hydrogen, which was the smallest and lightest thing known to humanity at the time. Let that settle in for a moment. This meant that the electron was smaller than the atom. Dalton's very first rule that the atom was the ultimate, indivisible, uncuttable piece of matter had just been beautifully, quietly broken. The atom had pieces. To prove this wasn't just a strange property of one specific material, Thomson changed the metal plates inside his glass tube. He used iron, then copper, then aluminum. No matter what metal he used, the exact same glowing beam of identical, lightweight, negative electrons appeared. He realized that these tiny negative sparks must be a fundamental part of all atoms in the universe. But this created a fascinating puzzle for Thomson. He knew that atoms, in their natural resting state, are electrically neutral. They do not shock us when we touch them. If an atom contains these tiny negatively charged electrons, there must be a positive charge somewhere inside the atom to perfectly balance it out. To explain this, Thomson proposed a lovely, comforting new picture of the atom, which became known affectionately as the plum pudding model. Imagine a warm, soft, round cake made entirely of a positively charged dough. Now, imagine those tiny, negatively charged electrons scattered throughout that soft, positive cake, much like sweet, dark raisins gently baked into a comforting dessert. The positive cake and the negative raisins perfectly cancel each other out, leaving the whole atom peacefully neutral. It is almost impossible to overstate how deeply this single discovery shapes the very fabric of your life today. That tiny, glowing green ray in Thomson's quiet laboratory was the exact same phenomenon that makes our modern world possible. The electron is the ultimate mediator of energy and connection. When you flip a switch and a room is instantly flooded with warm light, you are commanding a river of electrons to flow through a wire. When you gently rub a balloon against a soft woolen sweater and feel the quiet crackle of static electricity, you are physically brushing these tiny electrons from one surface to another. The device you are using to listen to my voice right now is entirely dependent on the incredibly precise, choreographed dance of millions of electrons moving through microscopic pathways. Even more profoundly, the gentle, rhythmic beating of your heart and the quiet thoughts drifting through your mind as you fall asleep are carried by the flow of electrical charges in your body. We are, in a very real sense, electrical beings, intimately connected to the very spark Thomson found hiding inside the solid atom. J.J. Thomson forever changed our view of reality, replacing the hard, solid sphere of the past with a soft, positive cake filled with tiny negative sparks. It is a comforting image to hold on to as the night deepens, but in science, no answer is ever truly final. It is merely a bridge to the next beautiful question. As we rest here, we must wonder, was Thomson right? Is the atom truly a soft, continuous dough of positive charge? Let us hold that peaceful image of the plum pudding for now, a sweet and complete thought. For when we return to our journey, we will step into another laboratory, one that will shatter this soft cake entirely, revealing a stunning, silent emptiness hidden in the architecture of matter. Lesson 4. Discovery of the nucleus. Welcome back. In our previous session, we found a sense of comfort in J.J. Thomson's vision of the atom. We imagined a soft, warm plum pudding, a continuous, gentle sphere of positive dough dotted with tiny negative electrons. It was a peaceful image, a universe that felt completely filled and quietly balanced. But the beauty of science is that it never stops asking questions, and it never hesitates to look just a little bit closer. In this lesson, we must bid farewell to that soft, comforting cake. We are going to travel to the year 1911 and step into a darkened laboratory where a profound and shocking truth about our reality was waiting to be uncovered. We are going to witness an experiment that shattered the illusion of solid matter completely, revealing a vast, silent emptiness hidden right in the very center of everything we can touch and feel. Our guide for this leg of the journey is Ernest Rutherford, a brilliant, booming physicist from New Zealand with a boundless curiosity. Rutherford wanted to test Thomson's plum pudding model. He wanted to know exactly what it would feel like to push through that soft, positive dough. To do this, he needed a very tiny, very fast probe. He chose something called an alpha particle. You can think of an alpha particle as a minuscule, incredibly heavy, positively charged cannonball, naturally thrown off by certain radioactive materials. Rutherford's experiment was beautifully simple in its design. He took a piece of solid gold and patiently pounded it down until it was a foil so unfathomably thin that light could almost pass through it. It was merely a few atoms thick. Then, he set up a device to fire a steady stream of these heavy, positive alpha particles directly at the delicate gold leaf. Behind the gold foil, he placed a circular screen coated with a special chemical that would produce a tiny, faint flash of green light whenever an alpha particle struck it. Rutherford and his dedicated students sat in the pitch-black laboratory, allowing their eyes to adjust to the dark, and began to watch the screen. According to Thomson's plum pudding model, the gold atoms were just soft clouds of positive charge. Therefore, Rutherford expected these heavy, fast-moving alpha cannonballs to tear right through the soft gold tissue paper without any trouble at all. And for the most part, exactly as expected, they saw thousands of tiny green flashes lighting up directly behind the foil. The particles were sailing smoothly through the gold, as if it were barely there. But then, something impossible happened. Every so often, a flash would appear off to the side. And then, defying all logic, a flash illuminated the screen completely backward, on the same side as the alpha particle source. Some of the particles were not going through the soft dough at all. They were ricocheting wildly off to the sides, and a few were bouncing straight back at the experimenters. Rutherford was utterly astounded. He later described the shock of this moment with a famous and perfect analogy. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you. How could this possibly happen?" Rutherford spent months quietly agonizing over this impossible result. The soft, continuous dough of Thomson's atom could never cause a heavy, speeding alpha particle to reverse its course. The only logical conclusion, Rutherford realized, was that the plum pudding model was completely wrong. The positive charge of the atom, and almost all of its heavy mass, was not spread out softly like a cake. Instead, it was crushed and concentrated into an unfathomably tiny, incredibly dense point at the absolute dead center of the atom. He named this heavy, dense center the nucleus. Because the nucleus was so dense and strongly positive, whenever a positive alpha particle happened to strike it dead on, the intense repulsive force of two positive charges meeting caused the heavy alpha particle to bounce violently backward. But because this only happened a few times out of tens of thousands of flashes, it meant that the nucleus was unimaginably small. To truly understand the scale of what Rutherford discovered, we must use our imagination. Picture yourself standing in the very center of a massive, sweeping sports stadium. Imagine taking a single, small glass marble and setting it down gently exactly on the 50-yard line. That tiny marble is the nucleus. It contains virtually all the weight and all the positive charge of the atom. Now, look up at the highest, most distant rows of seats curving around the edges of the stadium. That is where the tiny, negative electrons are buzzing and swirling. And what exists in the vast, echoing expanse between that solitary marble on the grass and those distant seats? Absolutely nothing. Pure, unadulterated, silent, empty space. In a beautiful twist of fate, the ancient philosopher Democritus, who dreamed of atoms swirling in an infinite void, was proven right once again, but the void wasn't just between the atoms. The void was inside them. This discovery changes the way we must view the entire physical world. It tells us that the illusion of solidity is exactly that, an illusion. Think about the heavy, solid chair you might be sitting on, the warm blankets resting over your shoulders, or even your own hands resting gently at your sides. Because you are made of atoms, and atoms are overwhelmingly made of empty space, you yourself are almost entirely composed of nothingness. If we were to somehow remove all the empty space from the atoms of every single human being on Earth, collapsing those distant electrons right down onto their central marbles, the entire human race, all 8 billion of us, would easily fit into the volume of a single sugar cube. So why does the world feel solid? Why doesn't your hand pass right through the table? Because the electrons orbiting your hand and the electrons orbiting the table repel each other with an invisible electrostatic force field. When you touch something, You are not actually feeling solid matter touching solid matter. You are feeling the gentle, invisible push of magnetic fields interacting across the quiet void. You are feeling the shape of empty space, held in perfect, reliable balance by the forces of the universe. It is a deeply humbling and beautiful realization. Rutherford's brilliant intuition gave us the dense, heavy nucleus, sitting silently in the center of the vast atomic void. But a new question naturally arises. What exactly is that little marble made of? It cannot simply be a single, featureless dot of positive charge. There must be a structure hidden even deeper within. Let us hold this beautiful, starry emptiness in our minds for now, finding rest in the vast spaces within ourselves. When we resume our journey, we will walk softly into the center of the stadium and look closely at the fundamental characters that live inside the nucleus. Lesson 5. Subatomic particles, protons, neutrons, and electrons. Welcome back to our quiet space. In our previous sessions, we have taken a magnificent journey. We began with the ancient Greek dream of the uncuttable stone. We moved to John Dalton's perfectly solid sphere, and then we watched as Ernest Rutherford beautifully shattered that illusion. He revealed that the atom is not a solid object, but a vast, echoing expanse of empty space, with almost all of its weight resting in a tiny, impossibly dense marble at the absolute center, which he called the nucleus. Tonight, we are going to take the next natural step together. We are going to zoom in even closer. We will walk softly across that vast, empty stadium of the atom, directly to that tiny marble resting on the center grass. In this lesson, we will gently unpack that central point and finally meet the three fundamental characters that come together to build the entire universe. Every atom in existence, from the iron in your blood to the oxygen drifting gently into your lungs right now, is constructed from just three distinct subatomic particles. Let us introduce them slowly, giving each one the time and attention it deserves. First, we have the proton. The proton resides safely and securely deep inside the nucleus. It carries a strong, positive electrical charge. You can think of the proton as the anchor of the atom, the heavy, defining presence that gives an element its true identity. Second, we have the neutron. The neutron lives tightly packed right alongside the proton, intimately sharing the tiny space of the nucleus. The neutron is almost exactly the same size and weight as the proton, but as its name beautifully suggests, it is completely neutral. It carries no electrical charge at all. It does not push, and it does not pull. It simply rests there, adding weight and a quiet, profound stability to the center of the atom. Finally, we have the electron. We met this tiny, energetic particle when J.J. Thomson discovered it glowing in his glass tubes. The electron carries a negative electrical charge, exactly equal and opposite to the positive charge of the proton. But, unlike the heavy proton and neutron, the electron is vanishingly small and unimaginably light. And most importantly, it does not live in the nucleus. The electrons orbit far, far away from the center, moving endlessly through the vast, dark emptiness of the atom's outer reaches. To help visualize this arrangement, imagine a wide, open field deep in the quiet of winter, blanketed in a thick, soft layer of snow. In the very center of this vast field, huddled closely together for warmth, is a small, tight-knit group of people. Some of them are wearing bright, vibrant colors. These are the positive protons. Nestled right between them, holding them together and keeping the peace, are others wearing soft, quiet gray. These are the neutral neutrons. Together, they form the heavy, stationary campfire at the center of the field. Now, imagine tiny, fast-moving fireflies darting in wide, sweeping circles along the very distant edges of the dark woods, far away from the fire. These are the negative electrons, dancing lightly in the distance, drawn to the warmth of the center but destined to keep their wide, protective orbits. The story of how we found these three particles is a testament to human patience. After Rutherford discovered the heavy, positive nucleus, identifying the proton was relatively straightforward. Positive charge has a loud voice. In chemistry, it interacts strongly with magnets and electrical fields, making it easy for scientists to track and measure. But as scientists began to weigh different atoms, they encountered a deeply puzzling mystery. They knew how much a single proton weighed, and they could count the protons in an atom by measuring its positive charge. However, when they placed the atom on a metaphorical scale, it was always much, much heavier than the protons alone could account for. For example, a helium atom has exactly 2 positive protons, but it weighs as much as 4 protons. Where was this phantom weight coming from? What was hiding in the dark center of the atom? It took another 2 decades of quiet, persistent searching to find the answer. The mystery was finally solved in 1932 by an English physicist named James Chadwick. Chadwick discovered the neutron. The reason this particle had remained perfectly hidden for so long is because its lack of electrical charge made it utterly invisible to all the standard tools of the time. It wouldn't bend in a magnetic field, and it wouldn't move toward a positive or negative plate. It was a silent partner. Chadwick had to use ingenious, indirect collisions to finally prove it was there, sitting quietly next to the protons. We must also appreciate the sheer difference in mass between these particles. The proton and the neutron are the undisputed heavyweights of the atomic world. The tiny electron, dancing in the outer dark, is incredibly light by comparison. To understand this difference, imagine placing a single proton on one side of a scale. To make that scale balance, you would have to gently stack nearly 2,000 electrons on the other side. This is precisely why Rutherford's alpha particles bounce backward. Almost 100% of an atom's mass, its physical substance and weight, is entirely concentrated in those protons and neutrons huddled in that tiny, microscopic marble of the nucleus. Understanding these 3 specific particles, the proton, the neutron, and the electron, is the master key that unlocks the entirety of chemistry, biology, and physics. Nature has created a beautifully elegant division of labor among them, where each particle has a very specific, vital job to do. The number of protons an atom holds is its soul, its absolute identity. If an atom has 6 protons, it is carbon, the foundation of all living things. If it has 79 protons, it is glittering gold. The number of neutrons dictates the stability of the atom. Because positive protons naturally repel one another, a nucleus packed only with protons would violently blow itself apart. The neutral neutrons act as a soothing, nuclear glue, sitting between the protons and holding the heavy center peacefully together. Finally, the electrons dictate how the atom will behave and interact with its neighbors. Because the electrons live on the outermost edges of the atom, they are the parts that touch, share, and bond with other atoms, building the complex, beautiful molecules that make up the world we know. Now that we have formally met our 3 primary players, the heavy, positive proton, the quiet, neutral neutron, and the tiny, negative electron, we have all the building blocks necessary to construct the universe. But with so many elements in the world, each with different amounts of these particles, we need a simple, reliable way to count them and organize them. Let this knowledge settle softly in your mind, like the quiet fireflies circling the snowy field. Rest easily as we quietly transition to our next topic, where we will learn how chemists give every single atom its own unique, perfect number. Lesson 6. Atomic number and mass number. Welcome back. In our last session together, we stood in the center of the atomic void and finally met the three fundamental characters that build our universe: the heavy, positive proton, the quiet, neutral neutron, and the tiny negative electron dancing in the distance. We imagined them in a vast snow-covered field, finding their perfect balance. But with billions of these particles swirling around to create the endless variety of elements in the world, from the calcium in our bones to the iron deep within the earth, how does the universe keep track of it all? Tonight, we take the next step together and learn how chemists bring magnificent order to this subatomic wilderness. We are going to explore a beautifully simple numbering system, learning how we give every single atom its own unique, unchanging identity and weight. To understand how we organize atoms, I would like you to imagine a sprawling, magnificent, ancient library. Picture endless rows of tall oak bookshelves stretching into the distance, softly illuminated by warm, golden light. If you were to walk into this vast library looking for one specific book out of millions, you would be entirely lost without a system. You would need a catalog number, a unique identifier, telling you exactly where that book belongs. For atoms, this ultimate catalog number is called the atomic number. The atomic number, which scientists represent with the capital letter Z, is elegantly simple. It is merely the exact count of protons resting securely inside the nucleus of an atom. That is all it is, a simple tally of the positive charges. But its simplicity hides its profound importance. The atomic number is the absolute, unchanging identity of an element. It is the very soul of the atom. If you hold an atom that contains exactly one proton in its center, its atomic number is 1, and it is endlessly, undeniably hydrogen. If you add more protons until you have exactly 6, the atomic number becomes 6, and the atom is entirely transformed into carbon. If you pack 79 protons into that central marble, you have gold. You cannot change the number of protons without fundamentally changing the very identity of the element itself. Next, we have a second number to give us a fuller picture of the atom, called the mass number, which is represented by the capital letter A. If the atomic number tells us who the atom is, the mass number tells us how heavy it is. The mass number is simply the total, combined count of all the heavy particles living inside the nucleus. To find it, you simply count the protons, and then you add the count of the quiet, neutral neutrons sitting right next to them. You might picture this like preparing a sturdy backpack for a long journey. If you want to know how heavy the backpack will be, you count the heavy hardcover books. These are your protons. Then, you count the thick, heavy notebooks. These are your neutrons. You add them together to understand the total mass you will be carrying. The mass number is just that, the sum of the heavy things. You might naturally wonder, as we pack this metaphorical backpack, why we haven't counted the electrons. After all, the electrons are part of the atom too, aren't they? They certainly are. But we must remember the profound difference in weight we discovered in our last lesson. The electrons are vanishingly, almost impossibly light. Returning to our backpack analogy, if the protons and neutrons are heavy hardcover books and thick notebooks, a single electron is like a tiny, thin paper receipt tucked into the front pocket. If you have a backpack filled with 20 heavy books, adding or removing a tiny paper receipt does not noticeably change the weight of the bag. Because it takes nearly 2,000 electrons to equal the weight of a single proton, chemists simply ignore the electrons when calculating the mass number. The mass of the atom is entirely decided by that heavy, central nucleus. Let us look at a beautiful, concrete example. Consider a standard atom of carbon, the element that forms the basis of all life on Earth, including you and me. If we look deeply into its central nucleus, we will find exactly 6 protons. Therefore, its atomic number is precisely 6. Now, If we look just a little closer, we will see that nestled right alongside those 6 protons are exactly 6 neutral neutrons. To find the mass number, we perform the simplest math we learned as children. We gently add the 6 protons to the 6 neutrons, giving us a mass number of 12. Furthermore, this numbering system tells us about the invisible electrons, even without directly counting them in the mass. In a calm, resting, neutral atom, nature demands perfect balance. The total positive charge must be perfectly cancelled out by the total negative charge. So, if our carbon atom has 6 positive protons in its heart, we know with absolute certainty that it will gently hold onto exactly 6 negative electrons in its distant, swirling orbits. The atomic number quietly dictates everything: the identity, the charge, and the perfect, peaceful balance of the atom. This seemingly simple numbering system is one of the most powerful tools humanity has ever developed. It serves as the universal, unifying language of science, transcending all spoken languages and borders. A chemist working late at night in a laboratory in Tokyo, a geologist digging in the red dirt of Australia, and an astronomer peering through a telescope in the mountains of Chile can all read the exact same notation. When they see an atomic number of 8, they all know immediately and without any shadow of a doubt that they are dealing with oxygen. Just as a fingerprint uniquely and flawlessly identifies a person, the atomic number uniquely identifies an element. It removes all ambiguity, allowing medical researchers to perfectly synthesize life-saving medicines and materials scientists to engineer the alloys that build our modern world. It proves that beneath the messy, chaotic appearance of the physical world, there is a deep, mathematical rhythm. The universe is not random, it is countable, knowable, and beautifully organized. As you lie here, resting in the quiet, you can take comfort in this profound sense of order. The atomic number, the number of protons, is fixed, permanent, and eternally reliable. But nature, in her endless creativity, always loves to introduce a little bit of variety. While an element's protons can never change without changing the element itself, the number of quiet neutrons in the nucleus sometimes can, and does, fluctuate. The mass number can gently shift, giving us different, slightly heavier or lighter versions of the exact same element. Let us hold on to this peaceful thought, allowing the numbers to fade into the background. When we drift into our next subject, we will explore this fascinating variety and learn all about. Lesson 7. Isotopes. Welcome back. In our last session together, we found a profound sense of comfort in the absolute, unchanging rules of the atomic number. We learned that the number of positive protons in the center of an atom is its ultimate identity, a permanent truth that never wavers. If an atom has 6 protons, it is carbon, unconditionally and forever. But as we take our next step together tonight, we are going to explore a beautiful nuance in nature's design. Nature, in her endless creativity, loves a little bit of subtle variety. Tonight, we will discover what happens when an element keeps its strict identity, but gently changes its weight. We are going to explore the fascinating world of isotopes, learning how the quiet, neutral particles in the center of the atom can fluctuate, giving us different, subtly unique versions of the exact same element. To understand this concept, we must return our focus to the tiny, dense marble at the center of the atom, the nucleus. We know that the heavy, positive protons dictate the identity of the atom, and we know that the neutral neutrons sit quietly beside them, adding weight and keeping the peace. But here is the magnificent secret. While an element can never, ever change its number of protons, it can have a different number of neutrons. Isotopes are simply atoms of the exact same element that happen to have a different number of neutrons. Because they have the same number of protons, they are the exact same chemical element. But because they have a different number of neutrons, they have a different mass. They are a little heavier or a little lighter than their siblings. Let us use a comforting analogy. Imagine you are walking into a showroom of beautifully restored, classic, vintage cars. You see two cars of the exact same make, the exact same model, and the exact same deep, polished color. They have the same powerful engine, the same leather seats, and they drive down the road with the exact same smooth, elegant performance. To any driver, they are absolutely identical. However, resting quietly in the trunk of the second car is a very heavy, unseen suitcase. If you were to drive both cars, you would notice no difference at all. But if you were to place them both on a giant scale, the second car would register as slightly heavier. Isotopes work in the exact same way. Let us look closely at carbon, the essential building block of all life on Earth. Every single atom of carbon in the universe must have exactly 6 protons. That is the rule. And the vast, overwhelming majority of carbon atoms also have exactly 6 neutrons sitting in their nucleus. If we add those together, we get a mass number of 12. We call this version carbon 1,2. But occasionally, nature slips an extra neutron into the trunk. A small fraction of carbon atoms out in the world have 6 protons and 7 neutrons. This is carbon 1,3. And even more rarely, some have 6 protons and 8 neutrons, becoming carbon 1,4. They are all true carbon. They all bond the same way, they all form the same beautiful molecules, and they all act exactly the same in chemical reactions. They are just slightly heavier versions of the exact same classic car. The discovery of isotopes was a quiet revolution in the early 20th century. As chemists began to measure atomic weights with greater and greater precision, they noticed something deeply confusing. They found samples of what appeared to be the exact same element samples that behaved identically in every single chemical test they could dream up. But the samples had slightly different weights. In 1913, a brilliant English radiochemist named Frederick Soddy finally solved the puzzle. He realized that an element wasn't just one single, uniform weight, but could exist in multiple, different weighted forms. He needed a word to describe this new phenomenon. During a quiet dinner party, he explained his dilemma to a Scottish doctor and writer named Margaret Todd. She suggested a beautiful name drawn from ancient Greek. She combined the word isos, meaning equal or same, with the word topos, meaning place, isotope. The name is profoundly perfect. Because the periodic table is organized strictly by atomic number, the number of protons, all the different isotopes of an element belong in the exact same place on the table. Carbon 1,2, carbon 1,3, and carbon 1,4 do not get separate boxes. They are all roommates, sharing the exact same square on the periodic table because their chemical identity is identical. But this variation in weight introduces another fascinating layer to our story, the concept of stability. In the nucleus, the protons and neutrons exist in a delicate, perfectly balanced embrace. For many atoms, like carbon 1,2, this balance is absolutely perfect, and the atom is entirely stable. It will sit quietly in the earth, unchanging, until the end of time. However, if you pack too many neutrons into the nucleus, the delicate balance begins to wobble. The atom becomes slightly top-heavy, like a tower of blocks stacked just a little too high. We call these unstable isotopes radioactive, but the word radioactive need not be frightening here. It simply means the atom is seeking peace. Over time, an unstable isotope like carbon 1,4 will gently release that extra, restless energy, shedding a tiny piece of itself in a slow, predictable process called radioactive decay, until it finally settles into a new, perfectly stable form. This gentle, predictable decay of unstable isotopes provides us with one of the most magical tools in all of modern science. High in our upper atmosphere, cosmic rays from the distant sun are constantly, softly creating tiny amounts of carbon, 1,4. This slightly heavier, unstable carbon drifts down to the Earth and mixes evenly into the air. As plants breathe in the air to grow, and as animals eat those plants, every living thing on Earth, including you and me, absorbs a tiny, predictable amount of this unstable carbon, 1,4, into our bones and tissues. As long as we are alive, the amount of carbon, 1,4, in our bodies remains perfectly steady. But the moment a tree falls in the forest, or a creature finally rests at the end of its life, it stops taking in new carbon. From that quiet moment onward, the unstable carbon, 1,4, trapped inside its cells begins to slowly, gently decay away, ticking down like a silent, invisible hourglass. Because scientists know the exact, unwavering speed at which this sand falls through the hourglass, they can look at an ancient piece of wood, a fragment of bone, or a scrap of woven cloth dug from the earth, and measure exactly how much carbon, 1,4, is left. By doing so, they can tell us exactly how long ago that living thing took its final breath. This beautiful process, known as radiocarbon dating, allows archaeologists and historians to literally read the clock of deep time, uncovering the long-forgotten history of our world, all because nature decided to put a couple of extra neutrons into the trunk of a carbon atom. As you rest here, feeling the steady, rhythmic beating of your own heart, you can marvel at the fact that you are beautifully composed of all these different, subtle variations of elements. You are a masterpiece of isotopes, living in perfect harmony. But this natural variety leaves us with a quiet, lingering question for our chemists. If carbon exists naturally as a mixture of carbon, 1,2, carbon, 1,3, and carbon, 1,4, what single number do we write down in that one shared box on the periodic table? How do we find the balance between them all? Let your mind drift peacefully on that thought. We will find the middle ground in our next lesson, where we will softly explore the mathematics of the average. Lesson 8. Average atomic mass. Welcome back. In our last session together, we explored the fascinating world of isotopes. We learned that while an element must always maintain its strict identity, its specific, unchanging number of protons, it is allowed a little bit of natural variety in its weight. We imagined these isotopes as identical, beautiful, classic cars, some of which happen to carry a slightly heavier suitcase of neutrons in their trunk. But this beautiful, natural variety leaves us with a quiet, lingering question. If elements out in the real world exist as a mixed-up blend of these slightly different weights, what single number do we write down to represent them? How do scientists agree on a single mass for an element? Now, we take the next step together and learn how we find that peaceful middle ground. We are going to explore the concept of average atomic mass. To understand how we find this middle ground, I want you to imagine opening a heavy, beautifully bound textbook and looking at a large, brightly colored periodic table of elements. If you were to look closely at the little box for carbon, you would see its atomic number, 6, resting neatly at the top. But if you look at the mass number, usually printed at the bottom of the box, you will not see a clean, perfect whole number like 12. Instead, you will see a somewhat messy, trailing decimal, 12.011. If you look at chlorine, you will see its mass is listed as 35.45. Why are these numbers so delightfully imperfect? Because the atomic mass listed on the periodic table is not the weight of one single, specific atom. It is an average. But it is not a simple, straightforward average. It is what mathematicians call a weighted average. It is a number that beautifully reflects exactly how common each isotope is in the natural world. Let us explore this idea with a simple, familiar analogy. Imagine a quiet, sunlit schoolhouse in a small village. In this schoolhouse, there is a large classroom filled with exactly 100 students. Now, imagine that 99 of those students are exactly 12 years old. Only one single student in the entire room is 13 years old. If someone were to ask you for the average age of a student in that room, you wouldn't just take the two ages 12 and 13 and cut them straight down the middle to say the average age is 12 and a half. That wouldn't be an honest reflection of the room at all. Because the 12-year-olds so heavily outnumber the solitary 13-year-old, their sheer numbers pull the true average heavily toward them. If you were to add up all of their ages and divide by 100, the true, weighted average age of that classroom would be 12.01. The average is overwhelmingly influenced by the most abundant group. Nature behaves in the exact same wonderfully mathematical way. When an element is formed in the heart of a dying star, nature doesn't create equal amounts of every isotope. Some versions are incredibly stable and common, while other, slightly heavier or lighter versions are vanishingly rare. Let us look deeply at our old friend, carbon, to see how this plays out in the physical world. In nature, the incredibly stable carbon, 1,2, the isotope with 6 protons and 6 neutrons, makes up about 98.9% of all the carbon on planet Earth. It is the overwhelming majority. Carbon, 1,3, which carries 1 extra neutron, makes up only about 1.1% of the world's carbon. And carbon, 1,4, with its 2 extra neutrons, is so unbelievably rare that it barely registers as a fraction of a percent. To find the average atomic mass, chemists perform a gentle mathematical blending. They take the exact mass of carbon, 1,2, and multiply it by its overwhelming fractional abundance, which is 0.989. Then, they take the slightly heavier mass of carbon, 1,3, and multiply it by its tiny fractional abundance of 0.011. When they gently add those pieces together, the heavy, dominant presence of carbon, 1,2, pulls the final average strongly toward itself, giving us the number we see on the periodic table, 12.011. Let us look at another beautiful example, chlorine. Chlorine is a fascinating element because it has 2 very common, stable isotopes. In nature, if you were to gather a handful of chlorine atoms, roughly 75% of them would be the lighter version, chlorine, 3,5. The remaining 25% would be the heavier version, chlorine, 3,7. Notice that there is no chlorine, 3,6, to bridge the gap. Because the lighter chlorine, 3,5, is 3 times more abundant than the heavier chlorine, 3,7, the average is pulled closer to 35, but the heavy 37 pulls it up just enough to land the average, right at 35.45. What is truly profound about this is that if you were to somehow pick up a single, solitary atom of chlorine, it would never weigh 35.45. It would either weigh 35 or it would weigh 37. There is no such thing as an individual atom with an average weight. The decimal number on the periodic table does not describe a single, lonely atom. It describes the collective. It is a mathematical reflection of the crowd, the beautiful, perfectly blended mixture of the whole universe. You might wonder why scientists go through the trouble of calculating these weighted averages. Why does this decimal matter so much? It matters because we do not live in the microscopic realm. We live in a large, heavy, macroscopic world. Imagine you are a brilliant pharmacist or an industrial chemist working late in a laboratory to synthesize a life-saving medication. You need to measure out exactly 100 grams of carbon for your chemical reaction. You cannot use microscopic tweezers to sort out the billions of carbon, 1, 2 atoms from the carbon, 1, 3 atoms. That would be impossible. You simply scoop up a handful of black carbon powder from a jar and place it on a brass scale. Because the Earth is so ancient, and because its winds have blown, its oceans have churned, and its tectonic plates have ground together for billions of years, the isotopes of elements are thoroughly and perfectly mixed everywhere on the planet. Whether you mine carbon from a deep cave in South America or extract it from the air high in the mountains of Asia, that 98.9 to 1.1% ratio is virtually identical everywhere. The average atomic mass is the crucial bridge between the invisible world of individual atoms and the heavy, tangible world we can touch and measure. By using the average atomic mass, scientists can scoop up billions of trillions of atoms at once and know exactly how many atoms are in their hand, simply by weighing them. They do not have to worry about sorting the isotopes. They can trust that nature, over billions of years, has already perfectly, flawlessly pre-mixed the batch for them. And so, we have built a complete, profound understanding of the atom. We have watched it evolve from an ancient, uncuttable stone to a vast, echoing stadium. We have met its tiny, fundamental particles, we have learned how to number them, and we have learned how to average their natural, beautiful variety. Now that we have all of these individual pieces, it is time to look at the grand, sweeping map of how they are organized. Let the numbers and the math softly fade from your mind, resting securely in the background. Our next lesson will pull the camera back, revealing a magnificent tapestry, as we are introduced to one of the most beautiful achievements of human intellect. Lesson 9. Introduction to the Periodic Table. Welcome back. Up until this point in our journey together, we have spent all of our time looking deeply through a microscopic lens. We have examined the solitary atom, marveling at its vast internal emptiness, counting its heavy protons and neutral neutrons, and tracing the distant, swirling paths of its electrons. We have been closely studying the individual trees, but now we take a breathtaking step back to look at the entire magnificent forest. We are going to pull the camera away from the single atom to reveal the grand, sweeping map of matter itself. In this lesson, we will be introduced to one of the most beautiful and profound achievements of human intellect. We will explore how all the fundamental ingredients of the universe come together in perfect harmony as we begin our introduction to the periodic table. When you hear the phrase periodic table, you might instantly picture a large, colorful chart hanging on the wall of a science classroom. It looks like a slightly uneven brick wall, a grid of squares filled with letters and numbers. But it is so much more than a simple list or a poster. It is a masterpiece of organization, a reflection of the deep mathematical rhythm of nature. To truly understand this chart, we must first think about the word periodic. What does it mean for something to be periodic? It means that it operates in a repeating pattern, a predictable cycle that returns to a familiar starting point again and again. The seasons of the earth are periodic, shifting from the soft green of spring through the quiet snows of winter, only to blossom into spring once more. The phases of the moon are periodic, waxing to a brilliant full sphere and waning back to a dark, quiet sky every 28 days. The elements of the universe, it turns out, share this exact same kind of beautiful, cyclical rhythm. The periodic table arranges all the known elements in order of their atomic number, the number of protons resting in their center, which we learnt about in our previous sessions. We start at the very top left with hydrogen, which has an atomic number of 1. We move to the right to helium, which has 2. Then we drop down to the next row for lithium, with 3, beryllium with 4, and so on, reading the table gently from left to right, top to bottom, exactly as you would read the soft, even lines of a poem. But the true magic of the table lies in its shape. We do not just write the elements in one infinitely long straight line. Instead, we break the line and start a new row at very specific intervals. Why? Because, as you count up the atomic numbers, the chemical properties of the elements begin to repeat. After a certain number of elements, you suddenly find one that behaves almost exactly like an element you passed earlier. By breaking the rows and stacking them on top of each other, chemists ensure that elements with similar personalities and behaviors line up perfectly in vertical columns. It is a harmonious grid where the order of the numbers seamlessly matches the rhythm of nature. The story of how we discovered this beautiful rhythm is one of the greatest tales of scientific intuition. It brings us to the snowy, freezing winters of St. Petersburg, Russia, in the year 1869. Here, a brilliant and deeply passionate chemistry professor named Dmitry Mendeleev was struggling to write a textbook for his students. He wanted to find a way to organize the 63 elements known at the time so that his students could easily understand them. Mendeleev was a man who loved puzzles. To solve this one, he created a set of blank paper cards. On each card, he carefully wrote the name of an element, its atomic weight, and a list of its most important chemical traits, how it reacted with oxygen, how easily it melted, and what color it burned. For days, he sat at his heavy wooden desk in his quiet, softly lit study, arranging and rearranging these cards like a peaceful game of cosmic solitaire. He tried grouping them by weight. He tried grouping them by their reactions. He moved them back and forth, listening for the quiet music of the universe, searching for the underlying pattern. Legend has it that after 3 days and nights of working without sleep, Mendeleev rested his heavy head on his desk and fell into a deep dream. In that dream, he saw a grand table where all the elements fell perfectly into place as required. When he awoke, he immediately wrote down the pattern he had seen. But Mendeleev did something entirely revolutionary. As he laid out his cards, he noticed that sometimes, to make the chemical properties align properly in their vertical columns, he had to skip a space. Most scientists would have assumed their pattern was flawed. Mendeleev, however, had such profound, unwavering faith in the rhythm of nature that he left those spaces completely blank. He boldly announced to the scientific community that these empty spaces were not flaws in his table, but rather undiscovered elements, pieces of the universe that humanity simply hadn't found yet. He didn't just leave blanks. He confidently predicted exactly what those missing elements would look like, how heavy they would be, and how they would react, based entirely on the empty space they occupied in his grid. He called one of these missing puzzle pieces silicon, predicting it would be a grey metal that was slightly heavier than titanium. The scientific establishment was deeply skeptical, but a little over a decade later, in 1886, a German chemist discovered a new element, which he named germanium. When they measured germanium in the laboratory, its weight, its color, and its density perfectly, flawlessly matched the predictions Mendeleev had made years earlier. The blanks were filled. The rhythm was real. Mendeleev had not just organized the known world, he had successfully mapped the unknown. Today, Mendeleev's puzzle has grown. We now have 118 known elements, filling out a complete, solid block of the table, leaving no blanks behind. But the purpose of the periodic table remains exactly the same. It is not merely a chart to be memorized. It is the ultimate tool of discovery, the grand compass that guides all of modern science. When researchers are trying to invent a new, more efficient solar panel, or when pharmacologists are designing a new molecule to treat a disease, they do not have to guess which elements to use. They simply consult the map. If they are using an element that is too heavy, or too expensive, or too reactive, they can look directly above it, below it, or right next to it, on the table to find a sibling element that shares the exact traits they need, but with a slight, useful variation. The periodic table brings order to the chaos, proving that our vast, complex universe is built upon a foundation of elegant, reliable, and deeply beautiful rules. As you lie here, resting in the quiet, imagine that grand table spanning out before you like a map of a vast, unexplored world. We have seen how the grid was drawn, and we understand the rhythm of its numbers, but a map is meant to be explored. This beautiful table can be peacefully divided into broader territories, with rolling hills, deep valleys, and distinct landscapes. As we let the story of Mendeleev's cards gently drift from our minds, we prepare to zoom in on this map. When we return, we will begin to explore the three great, sweeping kingdoms of the periodic table and learn about the metals, the non-metals, and the quiet twilight elements that live between them. Lesson 10. Metals, non-metals, and metalloids. Welcome back. In our last session, we zoomed out from the microscopic world of individual atoms and looked at the grand, sweeping map of matter, the periodic table of elements. We learned how Dmitri Mendeleev arranged this map, listening to the deep mathematical rhythm of nature. Now, we take the next step together and begin to explore the geography of this beautiful map. Just as our Earth is divided into vast oceans, sprawling forests, and sweeping deserts, the periodic table is divided into three distinct territories. In this lesson, we will journey through these broad kingdoms, exploring the metals, the non-metals, and the quiet, twilight elements that live right on the border between them. Imagine the periodic table spread out before you like a beautiful, ancient parchment map. As your eyes sweep across it, from the far left all the way through the center, you are looking at a massive, dominant continent. This vast territory, which makes up roughly 80% of all known elements, belongs entirely to the metals. When you picture a metal, your mind likely conjures up a familiar image, something solid, something with a cool, gleaming surface that reflects the light. And you would be perfectly correct. With only one exception, the heavy, silvery liquid called mercury, all metals are solid at room temperature. They possess a beautiful, characteristic shine that chemists call luster. But their true magic lies in their physical grace. Metals are incredibly forgiving materials. They are malleable, meaning they can be gently hammered into incredibly thin, flat leaves without breaking. They are also ductile, meaning they can be smoothly drawn out into long, thin, continuous wires. And most importantly, metals are generous. They easily and effortlessly allow heat and electricity to flow right through them. Now, let your eyes drift to the far upper right corner of our map. Here, huddled together in a much smaller territory, we find the non-metals. If metals are the strong, shining foundation of the table, non-metals are the wild, varied, and colorful elements of the world. Unlike the metals, non-metals do not follow a single rule for their physical state. Some of them, like oxygen and nitrogen, are invisible gases drifting quietly through the room around you. One of them, bromine, is a dark, heavy liquid, and those that are solid, like sulfur or phosphorus, are the complete opposites of metals. They are entirely dull, lacking any metallic shine. If you were to strike a solid non-metal with a hammer, it would not bend or flatten. It would simply shatter into a crumbly, jagged powder because they are exceedingly brittle. Furthermore, non-metals are deeply protective of their energy. They are insulators, stubbornly refusing to let electricity or heat pass through them. Finally, separating these two vastly different kingdoms, there is a quiet borderland. If you look closely at the right side of the table, you will see a jagged, descending boundary, like a staircase stepping down through the elements. Sitting gently right along this staircase are the metalloids. These are the twilight elements. They exist in the middle ground, refusing to be placed strictly into either category, beautifully sharing the traits of both. They are the chemical mediators of the universe, possessing a blend of characteristics that make them entirely unique and profoundly important. To truly appreciate these three kingdoms, let us look closely at a resident from each one. Think of a pure, polished copper bowl resting on a sunlit table. Copper is a classic, exemplary metal. If you were to pour hot tea into that bowl, the outside of the copper would become warm almost instantly. If you were to attach a wire to it, electricity would race through it without hesitation. Why do metals do this? It all comes back to the tiny electrons we learnt about in our earlier lessons. In a piece of solid metal, the atoms do not hold on to their outermost electrons tightly. Instead, they release them into a shared, gently flowing pool, often called a sea of electrons. Because these tiny negative charges are free to drift and flow effortlessly from atom to atom, they carry electrical currents and thermal heat right along with them, like water flowing down a wide, smooth river. This shared sea is also what allows the metal to bend without breaking. The atoms can slide past one another, cushioned by the fluid electrons. Now, let us imagine a chunk of pure sulfur, a classic non-metal. Sulfur is a pale, earthy yellow solid. If you tried to polish it, it would remain stubbornly dull. If you tried to wire it to a battery, nothing would happen. This is because non-metals hold onto their electrons with a fierce, tight grip. There is no flowing sea here. The electrons are locked securely in place, firmly bound to their specific atoms. Because the electrons cannot move, the electrical current is stopped completely in its tracks. And because the atoms are locked in rigid, inflexible positions, any sudden force simply cracks the structure apart, making it brittle. But what about our twilight elements? Let us look at silicon, the most famous of the metalloids. If you hold a piece of pure silicon in your hand, your eyes will tell you it is a metal. It is deeply shiny, with a beautiful, silvery blue metallic luster. But if you were to drop it on a stone floor, it would shatter exactly like glass, revealing the brittle nature of a non-metal. Its most magical property, however, lies in how it handles electricity. At room temperature, silicon behaves mostly like a non-metal, acting as an insulator. But if you gently apply just the right amount of heat, or just the right electrical voltage, silicon suddenly changes its mind. It opens the gates and allows a small, perfectly controlled amount of electricity to flow through. It is not a full conductor, and it is not a full insulator. It is a semiconductor. This quiet, twilight ability of the metalloids has profoundly shaped the entire landscape of human history. The unique nature of silicon, the ability to act as a precise, controllable gate for electricity, is the foundational secret of the modern digital age. Every computer, every smartphone, every satellite softly orbiting our Earth relies entirely on microscopic switches made of silicon. By perfectly controlling that slight electrical conductivity, engineers can process information, storing our memories, our voices, and our collective knowledge on tiny chips carved from this borderland element. At the same time, we must look at our own physical bodies. While the metals build our bridges and carry our power, and the metalloids run our technology, it is the non-metals that give us life. You are overwhelmingly made of non-metals. The carbon that builds your cells, the oxygen moving through your blood, the hydrogen in the water that sustains you, these dull, brittle, and gaseous elements, are the very canvas of biology. We live precisely at the intersection of these magnificent kingdoms, relying on the metals to build our world, the metalloids to connect it, and the non-metals to breathe life into it. As you lie here, resting peacefully, imagine the elements interacting all around you, each playing its perfect, destined role. We have explored the broad continents of the periodic table, but like any good map, there is always more detail to uncover. These large regions give us a wide, beautiful view, But the table has even more specific families and neighborhoods waiting to be explored. Let the broad kingdoms slowly fade into the quiet background of your mind. As we continue on our journey, we will zoom in slightly tighter, gently tracing our fingers down the vertical columns and across the horizontal rows that bring absolute, predictable order to the chaos. Lesson 11. Groups and periods of the periodic table. Welcome back. In our last session together, we stood high above the periodic table, looking down at the broad, sweeping continents of the metals, the non-metals, and the twilight metalloids. We saw the vast geography of matter laid out in beautiful, broad strokes. But as any traveler knows, to truly understand a place, you must eventually come down from the mountain and walk its streets. Now, we take that gentle step downward. We are going to navigate the specific avenues and neighborhoods of this magnificent map. In this lesson, we will explore the precise rows and columns that give the periodic table its supreme predictive power, discovering how the elements are bound together by deep, familial ties. To truly appreciate this beautiful order, I would like you to imagine the periodic table as a grand, meticulously planned city. The city is laid out in a perfect grid, composed of horizontal streets and vertical avenues. Let us first look at the horizontal streets, which chemists call periods. There are exactly 7 periods in our periodic city, stacked neatly from top to bottom. As you gently read across a single period, moving from left to right, you are watching a beautiful, continuous story unfold. With each step to the right, the atoms gain exactly 1 proton in their nucleus and 1 electron in their outer orbit. Because of this slow, steady addition, the properties of the elements change in a smooth, continuous spectrum across the row. You begin on the far left with highly reactive, solid metals, and as you stroll along the period, the metallic nature softly fades away, transitioning through the brittle metalloids until you finally reach the invisible, gaseous nonmetals on the far right. Every horizontal period tells this exact same story of transition, a gentle fading from solid metal to ethereal gas, over and over again. But the true magic, the absolute genius of Dmitri Mendeleev's design, reveals itself when we look at the vertical avenues. Chemists call these vertical columns groups, or more affectionately, families. There are 18 of these vertical groups in the main body of the table. When you move up and down a single vertical column, you are no longer watching properties change and fade. Instead, you are looking at elements that share a striking, unmistakable resemblance to one another. Think of a human family tree. A grandparent, a parent, and a child might be very different in their size, their weight, and their age, but they often share the exact same unmistakable color of eyes, the same shape of a smile, or the same distinctive laugh. Chemical families work in the exact same way. The elements in a vertical group are different sizes and weights, with the lightest at the top and the heaviest at the bottom, but they share the exact same chemical personality. They bond in the same way, they react to water in the same way, and they form the same beautiful geometric crystals. To know one member of a chemical family is to intuitively understand them all. To see these family personalities come to life, let us stroll down the very first street on the far left edge of our map. This vertical column is Group 1, intimately known as the alkali metals. This family includes elements like lithium, sodium, and potassium. Their shared personality is one of extreme, almost joyful reactivity. They are so eager to interact with the world around them that they cannot be found in their pure form in nature. They are always holding hands with other elements. Furthermore, they are incredibly soft. You could take a solid block of pure sodium metal and effortlessly slice it in half with a simple butter knife, revealing a brilliant, gleaming silver interior. But you must be careful, because this family reacts violently with water and even with the invisible moisture resting in the air. To keep them calm, chemists must store them completely submerged in jars of quiet, clear mineral oil. Now, let us travel all the way across the map to the complete opposite side, to the far right edge of the table. This is Group 18, a family known as the noble gases, home to helium, neon, and argon. If the alkali metals on the left are frantic and highly reactive, the noble gases on the right are deeply calm, utterly content, and profoundly solitary. They are completely colorless, odorless, and invisible. They do not react with water, they do not catch fire, and they absolutely refuse to bond with any other elements. They simply drift peacefully through the world, perfectly stable and complete all on their own. Why do these families behave so differently? The secret lies in the tiny electrons dancing in the outermost reaches of the atom. Elements in the same vertical column possess the exact same number of these outer electrons. The alkali metals all have exactly one lonely outer electron, which they are desperately eager to give away, making them highly reactive. The noble gases all have a perfectly full, perfectly balanced set of outer electrons. They need nothing, they want nothing, and so they remain beautifully calm. The vertical column an element lives in tells you instantly how its outer electrons are arranged, revealing its deepest chemical desires. This brilliant vertical organization is not just a triumph of academic sorting, it is the ultimate predictive compass for all of science and engineering. Because the families are so reliable, a scientist does not need to memorize the individual behaviors of all 118 elements. They simply need to know the general traits of the family. Imagine an aerospace engineer trying to build a new, lightweight frame for an airplane. They might look at magnesium, a light and strong metal sitting in Group 2. But perhaps magnesium is just slightly too heavy for this specific part, or too expensive. The engineer does not have to search the entire world blindly for a replacement. They simply look directly down the vertical column, staying within the same family, and find calcium or strontium. Because these elements live in the same family, the engineer knows with absolute certainty that they will behave chemically just like magnesium, but with slightly different weights. We see this same familial reliability within our own bodies. Our nervous system relies heavily on the flow of sodium and potassium to send gentle electrical signals to our muscles, allowing us to breathe and move. Why does biology use both of these elements so interchangeably? Because sodium and potassium sit right next to each other in the alkali metal family. Our cells know that they can use these chemical siblings to perform the exact same vital tasks. The periodic table proves that the universe is not a chaotic jumble of random materials, but a perfectly organized, predictable, and beautifully rhyming masterpiece. We have spent all of our time so far looking at these elements, standing alone, charting their solitary families, and learning their individual personalities. We know who they are, and we know where they live in the grand city of the periodic table. But as we have hinted, the universe is a profoundly social place. Elements rarely stay isolated for long. As you let the image of our majestic, orderly grid softly fade into the quiet background of your mind, we prepare for a shift. Let us hold this peaceful understanding of the solitary atoms. When we return to our journey, we will finally see what happens when these families interact, when atoms reach across the void to hold hands, as we begin our exploration of chemical formulas and the beautiful molecular world. Lesson 12. Chemical Formulas and Molecular Models. Welcome back. Up until now, our journey has been one of mapping the solitary elements. We have looked at atoms sitting alone in their neat, orderly boxes on the periodic table, charting their families and learning their individual personalities. But as you look around the room you are resting in, you do not see isolated elements. The universe is a profoundly social, interactive place. In this lesson, We are going to explore how those solitary atoms finally leave their boxes and come together to build the breathtaking molecular world we actually live in. We will learn how chemists write the recipes for these combinations, and how we build beautiful physical models to see the invisible architecture of nature. Rarely in the vastness of nature do we find elements existing in perfect solitary isolation. While the noble gases prefer to drift alone, the vast majority of atoms are deeply driven to connect. They seek out other atoms, reaching across the microscopic void to bind together in incredibly specific, stable arrangements. When atoms hold hands in this way, they form a unified group that we call a molecule. To describe these molecules clearly and simply, chemists use a beautiful, universal shorthand known as a chemical formula. Think of a chemical formula as a perfect, flawless recipe. It uses the elegant, capitalized letters from the periodic table to tell us exactly which elemental ingredients are present in a molecule. But knowing the ingredients is only half of baking. You must also know the exact amounts. To tell us how many of each atom are needed, the formula uses tiny numbers placed gently at the bottom right corner of the elemental symbols. We call these tiny numbers subscripts. Let us look at the most famous, most comforting chemical formula in the world, H2O. That simple, beautiful formula is the recipe for water. The H stands for hydrogen, and the tiny 2 resting softly beside it tells us that there are exactly 2 atoms of hydrogen in this molecule. The O stands for oxygen. Because there is no tiny number written next to the oxygen, we quietly understand that there is exactly 1 atom of oxygen present. That simple formula quietly and definitively tells us that every single solitary molecule of water in the universe, whether it is falling as a gentle raindrop, resting in a deep, cool lake, or melting from a snowflake on your cheek, contains exactly 2 atoms of hydrogen and 1 atom of oxygen. If you were to change those numbers, even slightly, it would no longer be water. The chemical formula is nature's absolute unbending recipe. While a chemical formula is a perfect recipe, it only gives us a list of ingredients. It does not tell us how the molecule actually looks. Because molecules are so impossibly small, far beyond the reach of the most powerful optical microscopes, we cannot simply look at them to see their shape. To solve this, human imagination stepped in, and chemists developed different types of models to visualize these invisible, three-dimensional structures. We use 3 primary ways to draw or build them, and each model tells a different, important part of the molecule's peaceful story. The first is the structural formula. This is a 2-dimensional drawing on a flat piece of paper. You write the letters of the atoms, and you draw delicate, straight lines, connecting them to show exactly which atom is holding hands with which. It is like the architectural blueprint of a house. It shows you where the rooms are connected, but it doesn't give you a sense of the space. In a structural formula of water, you would see the oxygen in the center, with a single line drawn to a hydrogen on one side and another line drawn to a hydrogen on the other. To truly see the shape, we use the ball and stick model. Imagine holding a beautiful, vintage wooden chemistry set. You have smooth, painted wooden spheres representing the atoms, and you have small metal rods representing the invisible bonds between them. When you build water this way, a fascinating reality emerges. The oxygen sphere does not hold the hydrogen spheres in a straight line. Instead, the 2 hydrogens are pushed down, forming a soft, bent shape, much like a boomerang or a wide, gentle letter V. The ball and stick model allows us to see the exact angles and the true geometric architecture of the molecule reaching out into 3-dimensional space. Finally, we have the space-filling model. While the ball and stick model is wonderful for seeing the angles, it leaves too much empty space between the atoms. In reality, atoms do not sit far apart on the ends of rigid sticks. Their outer electron clouds gently overlap and squish together. A space-filling model pushes the spheres tightly against one another, abandoning the sticks entirely. It shows the true, bulky volume the molecule takes up in the world. When you look at a space-filling model of water, it looks like a soft, plump cloud, a single, unified entity, where the boundaries of the individual atoms have beautifully melted into one another. You might wonder why we spend so much time building these three-dimensional shapes. Why does the exact physical geometry of a molecule matter? It matters because the shape of a molecule dictates entirely how it will interact with the living world. The study of these shapes is the very foundation of modern medicine and biology. Within your own body, there are thousands of incredibly complex proteins sitting on the surfaces of your cells. These proteins act like incredibly intricate, three-dimensional locks. When pharmaceutical scientists design a new, life-saving medicine, they are not just mixing liquids in a beaker, they are acting as microscopic locksmiths. By looking at the ball and stick and space-filling models of a drug, they can see its exact physical shape. They painstakingly adjust the chemical formula, adding an atom here or removing an atom there, to change the shape of the molecule until it slides perfectly and seamlessly into the protein receptor on your cell, exactly like a beautifully cut key turning softly in a lock. The shape is the function. As you lie here, resting deeply, picture those soft, plump, space-filling models drifting peacefully through your mind, locking smoothly into place. A chemical formula, combined with these beautiful models, tells us exactly what is inside a molecule and how it takes up space in the world. But sometimes, when dealing with very large, complex molecules, nature likes to reduce things to their simplest, most fundamental patterns. Let us hold that quiet thought as we transition smoothly into our next lesson, where we will explore the elegant difference between a molecule's true identity and its simplest mathematical core. Lesson 13. Empirical and Molecular Formulas. Welcome back. In our last hour together, we explored how solitary atoms reach across the void to hold hands, forming the beautiful three-dimensional shapes of molecules. We learned how chemists write the perfect recipe for these molecules using chemical formulas, explicitly listing every single ingredient. But as we take our next step together tonight, we will discover that there is more than one way to write a recipe. Sometimes, nature builds molecules that are so large and delightfully complex that we must first look for the simplest underlying pattern before we can understand the whole. In this lesson, we are going to explore the elegant difference between a molecule's literal, absolute truth and its simplest mathematical core. We will learn to distinguish between the molecular formula and the empirical formula. In the quiet, meticulous language of chemistry, there are two primary ways we describe the composition of a molecule. The first is called the molecular formula. The molecular formula is the literal, undeniable truth of the molecule. It tells you the exact, total number of atoms that are physically present in one single, complete molecule. Let us use a comforting example from your daily life: glucose. Glucose is a simple, sweet sugar, the very molecule that courses gently through your bloodstream to give your cells energy. If you were to hold one single solitary molecule of glucose in your hand and carefully count every atom, you would find exactly 6 carbon atoms, exactly 12 hydrogen atoms, and exactly 6 oxygen atoms. Therefore, the absolute, true molecular formula for glucose is C6H12O6. It is a precise accounting of every piece of the structure. But sometimes, mathematicians and chemists like to step back and look at the fundamental pattern rather than the total sum. This brings us to our second type of recipe: the empirical formula. Think of the empirical formula as a reduced fraction, or the simplest possible ratio of the elements present. To find the empirical formula of glucose, we simply look at our numbers 6, 12, and 6. and find the greatest common number we can divide them all by. In this case, we can divide all of them cleanly by 6. If we divide 6 carbons by 6, we get 1. If we divide 12 hydrogens by 6, we get 2. And if we divide 6 oxygens by 6, we get 1. Our new, reduced formula becomes C1H2O1, or simply CH2O. This is the empirical formula. It no longer tells us the total number of atoms in the whole sugar molecule. Instead, it tells us the fundamental, repeating pattern. For every one carbon atom present, there will always be exactly 2 hydrogen atoms and 1 oxygen atom. Imagine you are looking at a vast, beautiful mosaic tiled floor in an ancient courtyard. If you were to walk the entire courtyard and count every single tile, concluding there are 6,000 blue tiles, 12,000 white tiles, and 6,000 red tiles, you have found the molecular formula. But if you were to simply kneel down, look closely at the floor, and realize the artist used a simple, repeating pattern of 1 blue, 2 white, and 1 red tile over and over again to build the entire courtyard, you have found the empirical formula. Both descriptions are perfectly true, but they describe the masterpiece in entirely different ways. You might naturally wonder, why do we complicate things by having 2 different names and 2 different formulas? Why not just use the molecular formula all the time, since it is the literal truth? The answer lies in the beautiful, quiet history of how human beings learned to analyze the world around them. Let us travel back in our minds to a dimly lit 19th century laboratory. Imagine a chemist who has just been handed a vial containing a mysterious, unknown white powder. They have absolutely no idea what the powder is, or what molecules are hiding inside it. Their early instruments were not powerful enough to magically zoom in and count the total number of atoms in a single molecule. The only thing they could do was perform a gentle process called combustion analysis. They would slowly burn the white powder and carefully trap the gases that were released. By weighing those trapped gases, they could figure out the exact percentages, by weight, of the elements that were inside the powder. They could determine, for example, that the powder was made of exactly 40% carbon, 6.7% hydrogen, and 53.3% oxygen. When they converted those weights into atomic ratios, the very first piece of information their instruments gave them was the simplest ratio, CH2O. The empirical formula was always the very first clue, the first whisper of data in a dark room. The word empirical comes from an ancient Greek word meaning derived from observation or experiment. The empirical formula is exactly that, the first fundamental truth derived from the chemist's initial experiment. To find the true, heavier molecular formula, the chemist would have to perform entirely separate, much more difficult experiments to weigh the entire, intact molecule. Once they found the total weight, they could multiply their simple empirical pattern up to match it. It is also wonderfully comforting to know that for many of the most essential molecules in the universe, the empirical formula and the molecular formula are exactly the same. Let us look again at our gentle friend, water, H2O. The ratio of hydrogen to oxygen is 2:1. Because you cannot divide 2 and 1 by any whole number to get a simpler ratio without breaking atoms in half, the formula cannot be reduced any further. For water, the simplest pattern and the literal truth are one and the same. This historical process of finding the empirical formula first is not just a relic of the past. It is a foundational technique that we still rely on today, even as we reach for the stars. When a robotic rover lands gently in the red, dusty craters of Mars, it extends a mechanical arm to scoop up a sample of alien soil. It places that soil into a tiny, onboard oven and slowly heats it, analyzing the gases that drift away. The rover cannot see the complete, intact molecules in that alien dirt. The very first transmission it sends back across millions of miles of empty, silent space is the simple ratio of elements it has found. It sends back the empirical formula. When geologists on Earth receive that transmission, they are looking at the core ratio of elements, the fundamental pattern of a world they have never set foot upon. It is the first critical clue in solving the cosmic puzzle of what minerals exist on other planets, and whether the building blocks of life might be hiding softly in the dust. We have spent these last hours watching atoms share their space to make beautiful, neutral molecules, learning how to write their true names and discover their simplest patterns. It is a peaceful, balanced view of the world. But the universe is also filled with dynamic energy, and sometimes an atom does not want to share. Sometimes an atom seeks stability by losing or gaining a piece of itself entirely, becoming deeply electrically charged. Let us hold this quiet understanding of molecules here, a complete and restful thought. As we drift into our next lesson together, we will softly explore this transformation, learning about the formation of cations and anions. Lesson 14. Formation of cations and anions. Welcome back. In our earlier lessons together, we found great comfort in the perfect, peaceful balance of the neutral atom. We learned that a resting atom possesses a flawless symmetry. The number of positive protons in the heavy center is perfectly matched by the number of negative electrons swirling in the vast outer darkness. The charges cancel each other out, leaving the atom completely neutral and quiet. We also saw how atoms can gently share these outer electrons, holding hands to form delicate neutral molecules like water or sugar. But the universe is driven by a deep, underlying desire for absolute stability. And sometimes, to find that ultimate, lasting peace, an atom must willingly break its perfect, neutral balance. In this lesson, we will explore this profound transformation. We are going to watch as atoms give away pieces of themselves, or pull in new pieces from the void, becoming deeply electrically charged in the process. To understand why an atom would purposely break its neutral balance, we must look to the tiny electrons that dance in the outermost edges of the atom's reach. Nature has a very specific rule for these outer electrons. An atom feels profoundly stable, calm, and complete when its outermost layer is perfectly full, which for most elements means holding exactly 8 electrons. This is the same quiet perfection we saw in the noble gases, which drift alone and content. But most elements on the periodic table do not start with a full outer layer. They are restless, always naturally seeking that perfect configuration. If an atom finds itself with just 1 or 2 extra electrons orbiting far away from the nucleus, making it feel unstable and unbalanced, it will seek to simply give them away. Imagine holding a heavy, cumbersome stone in your hand while trying to walk a long distance. The most natural thing in the world is to let it drop, to unburden yourself. When a neutral atom releases a negatively charged electron into the void, a fascinating mathematical shift occurs. It is now left with more positive protons anchored securely in its center than negative electrons orbiting its edge. Because the positive charges now outnumber the negative ones, the entire atom takes on a positive electrical charge. It has transformed into a positive ion, which chemists call a cation. You can gently remember this word by picturing the letter T in the middle of the word cation as a small, quiet plus sign. Conversely, imagine an atom that is incredibly close to perfection. It has 7 electrons in its outer shell and desperately needs just 1 more to reach that beautiful, stable 8. It will instinctively reach out and pull a wandering electron into its orbit. By gaining this extra piece of negative charge, the atom breaks its neutrality in the opposite direction. The negative electrons now outnumber the positive protons. the atom becomes a negatively charged ion. We call this negative ion an anion. The atom has grown slightly larger, wrapped in a newly acquired blanket of negative energy, finally finding the deep stability it was searching for. Where do these beautiful exchanges take place? We can look back at our magnificent map, the periodic table, to see the grand choreography of this exchange. Do you remember the broad, shining continent of the metals resting comfortably on the left side of the table? Those metals, like sodium, magnesium, and calcium, are the generous givers of the atomic world. Their outermost electrons are held very loosely, drifting far from the strong pull of the nucleus. These metals are entirely willing, even eager, to surrender those few outer electrons to the universe, smoothly transforming into radiant, positive cations. On the exact opposite side of the map, nestled in the upper right corner, are the nonmetals, like chlorine, oxygen, and fluorine. These nonmetals are the eager receivers. They hold on to their electrons with a fierce, tight grip, and they are constantly scanning the horizon for one or two more electrons to complete their outer shells. When they pull those electrons in, they transform into soft, heavy, negative anions. It is a beautiful, harmonious exchange, a perfect atomic symbiosis. The universe never wastes anything. An electron is never simply thrown away into the empty dark. It is always handed directly from an atom that needs to lose it, straight into the welcoming embrace of an atom that desperately needs to gain it. When a silvery atom of sodium meets a greenish drift of chlorine gas, the sodium willingly hands its single, burdensome outer electron directly to the chlorine. In that fleeting microscopic moment, the sodium finds peace by becoming a positive cation, and the chlorine finds peace by becoming a negative anion. Both atoms achieve the absolute stability they were searching for. They have lost their neutrality, yes, but they have gained a profound, lasting chemical peace. This invisible, elegant transaction happens billions of times a second all around us, silently shaping the physical properties of the Earth and the oceans. The creation of these charged particles is not just an abstract concept happening in a distant laboratory. It is the very spark of your own life, happening deep within you at this exact moment. When atoms become cations and anions, they are no longer neutral. They carry an electrical charge, and the movement of that charge is what we call electricity. When you hear doctors or nutritionists talk about electrolytes, they are simply using the medical word for these exact same ions. Every single time you move your arm to gently adjust your blanket, every time your eyes softly flutter close, and every single time your heart beats in your chest, it is a direct result of these charged particles flowing through your body. Deep within your nervous system, microscopic gates are constantly opening and closing, allowing a rushing tide of positive sodium cations and negative chloride anions to flow back and forth across the membranes of your nerve cells. This gentle, rhythmic flow of tiny electrical charges carries the signals from your brain all the way to your fingertips. Without the generous surrender of electrons to create cations and the eager acceptance of electrons to create anions, human thought, movement, and life itself would simply cease to exist. You are, in essence, a masterpiece of flowing electricity, powered by the beautiful imbalance of ions. We have watched single, solitary atoms gracefully gain or lose electrons to become ions, finding their perfect stability as cations and anions. But nature is endlessly creative, and sometimes she builds structures that are slightly more complex. What happens when a whole family of atoms binds tightly together and then, acting entirely as one unified group, takes on a single, shared electrical charge? Let us hold the peaceful image of the glowing, charged ions right here, letting their energy softly fade into the background. As we gently drift into our next lesson together, we will explore this beautiful layer of complexity, learning about the tight-knit families known as polyatomic ions. Lesson 15. Polyatomic ions. Welcome back. In our last hour together, we watched a profound and beautiful transformation. We saw how single, solitary atoms, in their endless search for perfect stability, willingly give away or accept tiny electrons. In doing so, they shed their perfect neutrality and become charged particles, transforming into positive cations and negative anions. It was a lovely, simple exchange between individual atoms. But nature is endlessly creative, and she rarely stops at the simplest solution. Now, we take the next step together and add a beautiful, harmonious layer of complexity to this story. We are going to watch what happens when a whole group of atoms binds tightly together first, and then, acting entirely as one unified entity, takes on a single, shared electrical charge. In this lesson, we will explore the tight-knit families of the atomic world known as polyatomic ions. To understand this concept, we must look closely at the word itself. In the quiet language of science, the prefix poly gently translates to many. Therefore, a polyatomic ion is simply an ion made of many atoms. Most of the ions we discussed in our previous session were monatomic, meaning they were formed from just one single atom, like a solitary piece of sodium or a single atom of chlorine. But sometimes, atoms prefer to travel through the world together. Several atoms will reach out and bond tightly to one another, overlapping their electron clouds and sharing their electrons in a strong, secure embrace. You can think of a polyatomic ion very much like a tight-knit family holding hands as they walk together through a vast moving crowd. The bonds that hold this family together are incredibly strong. They do not easily let go of one another. But here is the magnificent twist. When this little family of atoms finally finishes assembling itself and counts up all of its internal protons and all of its shared electrons, it realizes that the numbers do not perfectly balance. As a whole, unified group, the family finds that it has either a slight surplus of electrons or a slight deficit. Because of this imbalance, the entire family takes on an electrical charge. The charge does not belong to just one atom within the group. It belongs softly and equally to the whole family. If the group has one or two extra electrons overall, the entire cluster becomes a large, multi-atom anion with a negative charge. If the group is missing an electron, it becomes a large, multi-atom cation with a positive charge. Throughout the chaotic, swirling dance of chemistry, these tightly bound clusters travel together, behaving almost exactly like a single, very large, charged atom. They stay firmly holding hands, navigating the chemical world as one beautifully synchronized unit. To truly visualize these families, let us look gently at a few of the most famous and important polyatomic ions in nature. First, imagine the sulfate ion. In the quiet shorthand of chemistry, it is written as SO4, carrying a -2 charge. Picture a single, central atom of sulfur, resting quietly in the middle. Now, imagine 4 atoms of oxygen nestling intimately around it, completely surrounding and protecting the sulfur on all sides. They are covalently bound together, sharing their electrons in a perfect, 3-dimensional geometric shape called a tetrahedron, which looks much like a tiny, perfectly symmetrical pyramid. When this beautiful pyramid is completely assembled, the 5 atoms collectively possess 2 more electrons than they do protons, and so the entire pyramid carries a charge of -2. When a chemist watches a reaction involving sulfate, they do not see the sulfur and the oxygen break apart and go their separate ways. Instead, the entire pyramid moves as a single, unbreakable piece, weathering the storms of chemical reactions perfectly intact. Another wonderful example is the ammonium ion, written as NH4 with a positive 1 charge. Here, a single nitrogen atom is softly surrounded by 4 hydrogen atoms. As they lock their hands together to share electrons, they find they are short exactly 1 electron for the entire group. Thus, the whole family carries a gentle positive 1 charge. Historically, these polyatomic ions were a source of great mystery to early chemists. When scientists like Lavoisier and Berzelius first began carefully taking chemicals apart, they noticed these distinct clusters acting stubbornly as single units. They called them radicals, observing that they could move a sulfate group from one compound to another over and over again, without ever breaking the strong bonds between the sulfur and the oxygens. It taught us a profound lesson about the hierarchy of chemical strength. The bonds holding the polyatomic family together are fiercely strong, allowing the group to survive intact, while it uses its overarching electrical charge to gently interact with other ions in the wider world. These polyatomic families are not merely academic curiosities. They are deeply, profoundly essential to the cycle of life on our planet, particularly in the quiet, patient world of agriculture. Imagine a vast, peaceful field of soil, resting under the soft light of a spring morning. Hidden within the dark, cool earth are millions of these charged families. The nitrates, a polyatomic family made of 1 nitrogen and 3 oxygens carrying a negative charge, and the phosphates, a slightly larger family of 1 phosphorus and 4 oxygens, are the absolute bedrock of plant life. When a gentle rain falls, water seeps into the soil and dissolves these charged families, allowing them to float freely. The roots of a growing plant, sensing the electrical charge, gently pull these intact polyatomic families up out of the dark earth and into their stems and leaves. The plant does not want solitary atoms. It specifically needs these beautifully pre-assembled families to build its green leaves, its strong stalks, and eventually, the very DNA within its cells. Even within your own body, as you lie here resting, polyatomic ions are quietly doing their vital work. The hard, solid structure of your bones and teeth is built from a massive, repeating lattice of calcium atoms holding tightly onto phosphate families. The calcium carbonate that makes up the stunning, towering white cliffs of Dover, or the delicate shells of ocean creatures resting on the sea floor, are all constructed using the quiet, stabilizing power of these charged, multi-atom groups. They are the complex, harmonious building blocks that allow nature to construct the intricate architecture of the living world. As you breathe softly, picture these tiny, perfect pyramids and clusters, these tight-knit families of atoms holding hands, gently drifting through the dark soil and the deep oceans. We have now met all the charged characters of our atomic story. We have seen the single, solitary cations and anions, and we have met the complex, unified families of the polyatomic ions. But we know that opposite charges in the universe cannot ignore one another for long. They are destined to meet. Let the image of these floating families slowly fade into the quiet expanse of your mind. Hold that sense of peaceful anticipation, for when we return to our journey, we will finally watch what happens when a positive charge and a negative charge draw close to one another as we begin our exploration of ionic bonds. Lesson 16. Ionic bonds and ionic compounds. Welcome back. In our recent hours together, we have witnessed a profound transformation. We watched single atoms and tight-knit families of atoms willingly surrender or accept tiny electrons in their endless quest for perfect stability. We saw them shed their neutrality, blooming into positively charged cations and negatively charged anions. Until now, we have looked at these charged particles floating peacefully, but separately, in the void. But one of the most fundamental laws of nature is that opposite charges cannot ignore one another for long. They are destined to meet. Now, we take the next step together and watch what happens when these opposites finally draw close. We are going to explore the powerful, invisible embrace that holds the very crust of our Earth together as we begin our lesson on ionic bonds and ionic compounds. To understand this beautiful connection, we must look to a force that you have likely felt with your own hands. If you have ever held two strong magnets and slowly brought their opposite poles together, you know that there is a moment before they even touch where you can physically feel them pulling. It is an invisible, undeniable, and deeply powerful force reaching across the empty space. In the microscopic world of chemistry, this exact same force governs the behavior of charged atoms. It is called electrostatic attraction. Imagine a positive metal cation, perhaps a silvery atom of sodium that has just given away its outermost electron, drifting quietly through the dark. Now, imagine a negative non-metal anion, a softly glowing atom of chlorine that has just eagerly accepted an extra electron, drifting nearby. As these two oppositely charged particles float closer to one another, that invisible magnetic force takes over. The positive charge of the sodium and the negative charge of the chlorine pull violently and beautifully toward one another until they finally meet, locking together in a perfectly tight, unyielding embrace. This deep, electrostatic embrace is what chemists call an ionic bond. It is crucial to understand that an ionic bond is not a physical thing. There is no tiny stick, no physical string, and no shared material tying these two atoms together. The bond is purely the invisible, absolute power of opposite electrical charges holding each other close. But the story does not end with just two atoms. This invisible magnetic force does not only pull in one direction, it radiates outward in all three dimensions. If a single positive cation is floating in space, it will attract negative anions from the top, from the bottom, from the left, and from the right. And each of those newly arrived negative anions will, in turn, attract more positive cations to their open sides. Millions, billions, and trillions of these charged ions gather together, stacking upon one another in a vast, perfectly ordered, alternating three-dimensional grid: positive, negative, positive, negative. We call this massive, repeating architecture an ionic compound. The ions build themselves into a magnificent, flawlessly symmetrical structure known as a crystal lattice. It is a microscopic skyscraper of alternating charges, stretching out in every direction, held together by the quiet, unbreakable tension of opposites. To truly appreciate the magic of this crystal lattice, let us look deeply at the most famous ionic compound in human history, one that is likely sitting quietly in your kitchen right now: ordinary table salt, known to chemists as sodium chloride. The story of table salt is one of the most poetic transformations in all of science. It begins with pure sodium, which is a soft, silvery metal, so violently reactive that if you were to drop a small piece of it into a calm bowl of water, it would instantly burst into bright, dangerous flames. The other half of the story is pure chlorine, which in its natural state is a dense, pale green gas that is highly toxic to all living things. If you were to encounter either of these elements in their pure, neutral forms, they would be incredibly dangerous. But watch what happens when they meet. The volatile sodium desperately wants to lose an electron to become stable. The toxic chlorine desperately wants to gain an electron to become stable. In a fleeting, microscopic moment, the sodium hands its electron perfectly to the chlorine. The sodium becomes a positive cation, and the chlorine becomes a negative anion. Having achieved their perfect stability, they instantly lock together in an ionic bond. In that beautifully simple exchange of a single electron, their dangerous personalities completely vanish. The violent metal and the toxic gas transform entirely into a calm, white, perfectly safe crystalline solid that we can cheerfully sprinkle over our food. They have found total peace in their union. If you were to take a single, tiny grain of table salt and look at it under a powerful magnifying glass, you would see that it is shaped like a perfect, sharp-edged little cube. This macroscopic cube is a direct, literal reflection of the microscopic crystal lattice hidden inside it. Deep within that grain, the alternating sodium and chloride ions have stacked themselves into billions of microscopic cubes, building up layer by perfectly ordered layer until it is large enough for your eyes to see. Because the electrostatic attraction holding this vast grid together is so incredibly strong, ionic compounds are immensely resilient. The atoms refuse to let go of one another. This is why almost all ionic compounds are hard, rigid solids at room temperature. It takes a massive amount of thermal energy to force these ions to vibrate hard enough to break their magnetic embrace. If you were to place a handful of table salt into an iron frying pan and turn the stove to its highest heat, the salt would not melt. It would simply sit there, calm and solid, because its melting point is well over 1,000 degrees Fahrenheit. The ionic bond is a testament to the profound strength of opposing forces finding perfect balance. This invisible attraction does not just season our evening meals. It literally builds the solid foundations of our world. When you step outside and look at a towering, jagged mountain range, or when you pick up a smooth, heavy stone from the edge of a river, you are looking at the macroscopic result of ionic bonding. The vast majority of the Earth's crust is composed of crystalline ionic compounds. Even the most beautiful, breathtaking objects we pull from the Earth are born of this alternating grid. The deep, mesmerizing blue of a sapphire, the rich, vibrant red of a ruby, and the cool, clear green of an emerald, these precious gemstones are simply complex ionic compounds, where different metal cations and non-metal anions have locked together deep underground over millions of years. Their incredible hardness, their ability to softly capture and bend the light, and their perfect geometric facets are all a direct result of that quiet, orderly, unbreakable magnetic embrace occurring at the atomic level. When you admire a gemstone, you are admiring the flawless mathematics of the ionic bond. As you lie here, resting peacefully in the dark, picture those perfectly ordered, alternating grids of positive and negative, holding the mountains and the gemstones firmly together. It is a deeply comforting thought, knowing the earth beneath us is anchored by such a strong, reliable force. But ionic bonds require a permanent exchange. They happen only when one atom is willing to give its electron entirely, and the other is willing to take it completely. But what happens when neither atom is willing to give up a piece of itself? What if they both refuse to let go? The universe always finds a peaceful compromise. Let the image of the rigid, glowing crystal lattice softly fade from your mind. When we return to our journey, we will explore a softer, more collaborative relationship as we begin our study of covalent bonds. Lesson 17: Covalent Bonds and Molecular Compounds. Welcome back. In our last session, we witnessed the profound, unyielding power of the ionic bond. We watched atoms willingly give and take electrons, transforming into electrically charged ions that lock together in massive, rigid, alternating grids. It was a story of absolute surrender and unbreakable electrostatic attraction, building the hard, crystalline rocks and gemstones of our Earth. But the universe cannot be built entirely of rigid stone. For life to exist, nature requires softness, movement, and flexibility. Now, we take the next step together and explore a completely different kind of relationship. We are going to see what happens when atoms refuse to surrender their pieces, choosing instead to find a beautiful, collaborative compromise. In this lesson, we will explore the peaceful sharing of electrons, as we begin our study of covalent bonds and molecular compounds. To understand this softer, more collaborative bond, we must gently turn our attention back to the upper right corner of the periodic table, to the territory of the non-metals. Elements like oxygen, carbon, nitrogen, and hydrogen are deeply protective of their electrons. When two non-metals drift close to one another in the microscopic void, they face a quiet dilemma. They both desperately need just a few more electrons to fill their outermost shells and achieve that perfect, noble gas stability we have spoken of. However, neither atom is willing to give away the electrons it already has. They are evenly matched in their desire. There can be no giving and taking here. So, they do something wonderfully elegant. They compromise. As the two atoms float closer and closer, they allow their outermost, invisible electron clouds to gently touch and overlap. In that shared, overlapping space between them, each atom offers up one of its own lonely electrons. These two electrons pair up, and instead of belonging to just one atom, this new pair begins to orbit both nuclei. The electrons race in a fast, fluid figure eight, wrapping around one atom and then smoothly sweeping around the other, holding them together through a mutual, shared connection. This beautiful, cooperative sharing of an electron pair is called a covalent bond. The word itself holds the secret to its meaning. Co, meaning to share or act together, and valent, referring to the valence, or outermost, shell of the atom. When atoms hold hands in this way, they do not build an infinite, never-ending grid like the ionic compounds do. Instead, they form a closed, private, discrete group. Once the atoms have shared enough electrons to feel perfectly stable and full, they close their doors. They do not need to bond with any other atoms around them. This self-contained, independent little group of covalently bonded atoms is what we call a molecule, and when a substance is made entirely of these separate molecules, we call it a molecular compound. To truly visualize the nature of this bond, imagine two travelers caught in a cold, quiet winter night. They only have one thick, warm woolen blanket between them. If one person were to take the blanket entirely for themselves, the other would freeze. So, they sit close together and pull the single blanket over both of their shoulders. As long as they are both holding onto that shared blanket, they are bound together. They cannot simply walk away from one another without losing the warmth they both desperately need. The shared blanket is the pair of covalent electrons, and the warmth they feel is the absolute stability of a full outer shell. This creates a profoundly different physical reality than the ionic crystals we studied last time. Remember that in a grain of salt, every single atom is magnetically locked to the atoms on its top, bottom, left, and right, building a rigid skyscraper of charge. But in a molecular compound, the story is entirely different. Consider a glass of cool, clear water. Water is a molecular compound made of countless individual H2O molecules. Inside each individual molecule, the covalent bonds holding the one oxygen and two hydrogens together are incredibly strong, like our travelers gripping the blanket. However, the connection between one water molecule and its neighboring water molecule is incredibly weak. Because each molecule is a perfectly satisfied, closed system, they do not chemically bond to one another. They simply bump and slide past each other in the crowd. This is a magnificent realization. This is exactly why molecular compounds have such soft, yielding physical properties. Because the separate molecules are not locked into a rigid grid, they do not need massive amounts of heat to separate them. This is why many molecular compounds are soft, flexible solids that melt easily, like the gentle wax of a burning candle or the soft cocoa butter in chocolate. It is why molecular compounds can be beautifully fluid liquids at room temperature, pouring smoothly from a pitcher as the independent molecules slide effortlessly over one another. And it is why so many of them, like the oxygen moving gently into your lungs right now, are completely invisible, ethereal gases, with their molecules drifting entirely free and unconnected in the open air. If ionic bonding is the chemistry of the Earth's hard crust, covalent bonding is, without a doubt, the chemistry of life. Biology requires movement, adaptation, and complex architecture that can gently bend without shattering. If the atoms in our bodies were held together by rigid ionic grids, we would be stiff, unmoving statues of stone. Instead, you are a masterpiece of covalent sharing. Think of the DNA resting quietly in the center of every single cell in your body. That breathtaking, twisting double helix is an impossibly long, complex molecular compound containing billions of atoms, all holding hands through covalent bonds. The proteins that make your muscles stretch and contract, the oils that keep your skin soft, and the complex sugars that slowly release warm energy into your bloodstream as you sleep. All of these are massive, intricate webs of carbon, hydrogen, and oxygen atoms, sharing their electrons in perfect, peaceful harmony. The covalent bond allows nature to string atoms together into long chains, intricate rings, and folding sheets, weaving the incredibly delicate, flexible fabric of all living things. As you lie here, resting deeply in the quiet of the night, you can marvel at the grand toolbox of the universe. We have now learned how nature builds both the unyielding mountains and the delicate, breathing forests. We understand the rigid strength of the taken electron and the soft flexibility of the shared electron. We have brought our atoms together in every way possible. We only have one final peaceful task remaining on our journey. We have built these magnificent structures, but we do not yet know what to call them. So, as we approach our final lesson together, we will learn the formal, systematic language of the laboratory, softly exploring the rules of chemical nomenclature. Lesson 18. Chemical Nomenclature. Welcome back to the deep, quiet comfort of our shared sanctuary for what will be our final hour together in this series. Please, take one more deeply peaceful, intentional breath in. Feel the cool, calm air fill the very bottom of your lungs, holding it just for a soft moment, and then let it wash out of you with a long, gentle, and completely relaxing sigh. Allow your head to rest as heavily as possible on your pillow. Let the muscles around your eyes and jaw completely soften, untensioning every part of your body, and simply allow my voice to anchor you in this perfectly still moment. Look at how far we have traveled. We began our journey on the ancient, sun-warmed shores of Greece, pondering the unbreakable stone. We wandered through the vast, echoing empty space of Rutherford's atom. We counted the heavy protons and neutral neutrons in the quiet dark of the nucleus, and we mapped the grand, rhythmic continents of the periodic table. Finally, we watched those solitary atoms reach across the microscopic void, giving, taking, and sharing their electrons to build the breathtaking structures of our world. We have built a universe, but a universe is not truly understood until it can be spoken of. In this final, quiet lesson, we are going to learn the formal, systematic language of the laboratory. We will softly explore the rules of chemical nomenclature, learning how to give every beautiful creation its proper, true name. The phrase chemical nomenclature might sound formal or imposing, but it is truly nothing more than the gentle, logical system we use for naming chemicals. It is a set of quiet rules that ensures every single molecule in the universe has a name that perfectly describes exactly what is inside of it. Let us break it down softly, beginning with the ionic compounds. We learned about those rigid, beautiful grids made of a metal and a non-metal locking together. For these ionic compounds, the rule is wonderfully, elegantly simple. You give the compound a two-word name, very much like a first and a last name. The first name is simply the exact name of the metal cation, entirely unchanged. The second name belongs to the non-metal anion, but to show that it has been bonded and transformed, we gently change the very end of its name to the suffix "ide." Let us practice this together. If you take the silvery metal known as sodium, and you bond it to the green gas known as chlorine, the metal keeps its first name, sodium. The chlorine changes its ending, becoming chloride. Put them together, and you have sodium chloride. It is a perfectly clear, deeply logical name. If you bond magnesium and oxygen, it becomes magnesium oxide. If you bond calcium and fluorine, it becomes calcium fluoride. The name is a transparent window, showing you exactly which two elements are holding on to each other in the dark. But what about our molecular compounds, where two stubborn nonmetals are peacefully sharing their electrons? Because nonmetals are so flexible in their sharing, they can combine in many different ratios. Carbon and oxygen, for example, can share electrons to form a molecule with one oxygen atom, or an entirely different molecule with two oxygen atoms. Simply calling them carbon oxide would not be enough. We need to know exactly how many atoms are present. To solve this softly and clearly, chemists use ancient Greek prefixes to count the atoms right there in the name. Mono means one, di means two, tri means three, and tetra means four. So, if a single carbon atom is peacefully sharing electrons with a single oxygen atom, we use the prefix for one, calling it carbon monoxide. But if that same single carbon atom is sharing its electrons with two oxygen atoms, the name gently shifts to reflect the new geometry, becoming carbon dioxide. The prefixes act as a microscopic map, telling you not just the ingredients, but the exact, perfect recipe of the molecule. There is a special, quiet subcategory in our naming system that deserves a moment of our time: the acids. Acids are fascinating molecular compounds that almost always begin with a hydrogen atom. When they are in a gas or solid form, we name them using our standard rules. Hydrogen and chlorine gas bonded together is simply called hydrogen chloride. But when you take that gas and gently dissolve it into a calm pool of water, something magical happens. The molecule changes its behavior, taking on a sour, reactive nature that we call acidic. To reflect this profound change in personality, the rules of nomenclature tell us to transform its name. We add the prefix hydro, change the ending to ic, and add the word acid. And so, hydrogen chloride melting into water beautifully becomes hydrochloric acid. To truly appreciate the deep peace and logic of this naming system, we must look backward to a time before it existed. Prior to the late 18th century, chemistry was a chaotic, disorganized landscape born of ancient alchemy. The names given to chemicals were poetic, but entirely confusing and secretive. A scientist in one country might be working with a substance called butter of arsenic, while another was using flowers of zinc, and yet another was pouring a liquid known terribly as oil of vitriol. None of these beautiful but messy names gave any clue whatsoever as to what the chemicals were actually made of. In the late 1700s, a brilliant and meticulous French chemist named Antoine Lavoisier, widely considered the father of modern chemistry, decided that this chaos had to end. He and a small, dedicated group of colleagues sat down in Paris and completely rewrote the language of nature. They stripped away the mysterious alchemy and created the precise logical rules of nomenclature that we just learned. Lavoisier believed deeply that the language of science should be a mirror of nature itself, clear, transparent, and completely truthful. By creating this system, he ensured that scientists around the globe, regardless of their native spoken tongue, were finally speaking one unified language. This quiet, logical language is not trapped inside the walls of a laboratory. You interact with Antoine Lavoisier's beautiful system every single day of your life. When you wake up in the morning and read the ingredient list on a box of breakfast cereal, or when you turn over a bottle of shampoo, or when you carefully read the label on a life-saving medication, you are reading the exact nomenclature rules you just learned. When you look at a label and see calcium carbonate or sodium fluoride, it is no longer a mystery. The words are no longer a confusing jumble of scientific jargon. Because of the journey we have taken together, you can look at those words and see the absolute truth of reality. You know exactly what atoms they contain. You know where those atoms live on the periodic table. You know whether they are giving, taking, or sharing their tiny electrons. And you know how they are holding together in the quiet, microscopic dark. Understanding this language pulls back the curtain of the world, revealing a universe that is not random or frightening, but rather knowable, organized, and deeply, profoundly beautiful. And so, my friend, our grand journey through the foundations of chemistry comes to a peaceful close. We have built a universe together, from the smallest, ancient, uncuttable atom to the heavy nucleus, all the way to the complex, named molecules that make up the breath currently moving so softly through your lungs. You have done wonderful work. Now, there is nothing left to learn, and absolutely nothing left to do. Let the names, the formulas, and the atomic numbers slowly melt away, like snow falling quietly onto a dark, warm field. Let the knowledge settle softly into the deep recesses of your mind, a permanent, quiet comfort. The atoms within you are resting, the universe around you is resting. And now, it is time for you to do the same. Rest perfectly, sleep deeply, and be at peace. Good night.